Hello, guys. I'm learning differential geometry, and now we will talk about tensors. I will see the videos, and I can share screen. Um, this is by a YouTuber called Chris, and let's start. Meanwhile, I'm using Gemini in order to understand the videos as well. Okay, so the next video, Tensor for Beginner 0, will be the tensor definition. And we would use formal math in order to define tensors.
In this video, I'm going to try and explain what exactly tensors are. So tensors are a little hard to describe if you've never heard of them before. So what I'm going to do is I'm going to give you several different definitions that you might hear from different people when you ask them what a tensor is. And hopefully seeing all these different points of view will put you in a good starting position so that you feel comfortable when we actually start doing real math in the next video. Okay, so let's get started. Here's a first attempt at a definition for tensors. I'll just read it off. So a tensor is a multi-dimensional array of numbers. And by array, I basically just mean grid. So a grid of numbers. Okay, so let's see some examples of what this might look like. So the simplest example of a tensor is what we would call a scalar, or sometimes a rank 0 tensor. And a scalar is basically just a number. So any number like 1, 2, 5, 3/4, pi, these are all examples of scalars. And we don't normally write scalars as arrays, but if we wanted to, we could write little square brackets around the scalar like this and sort of pretend it's an array, but we don't normally do that. All right, so those are scalars. Another example of a tensor you've hopefully seen before is a vector, or a rank 1 tensor. And we call it a rank 1 tensor because it's a list of numbers that extends downward in one dimension. So it's like a one-dimensional array. So that's a vector. Another example you've probably heard of are matrices, or rank 2 tensors, and we call them rank 2 because they are a two-dimensional grid of numbers, so they extend up, down, left to right. And if you recall from the last video, I mentioned that the metric tensor from general relativity is a rank 2 tensor. And these little Greek letters that you see here actually stand for numbers that represent the row and column of the particular entry of the matrix that we're talking about. So the metric tensor is really just a matrix. And we can go higher and higher. This is a rank 3 tensor because it's in a three-dimensional
Looks like
grid of numbers
some kind of
arranged
cube.
in a cube.
So
And we
have
can go on and on,
three
rank 4, 5, 6,
options
as high as we want.
how we go.
So any multi-dimensional array of numbers is a tensor. So I call this the array definition of tensors. Okay, so I said that this was a first attempt at a definition, and it does give us some idea of what a tensor is, but this definition is actually wrong, and here's why. So tensors can be represented as multi-dimensional arrays, but that's not what they fundamentally are. Tensors aren't just a bunch of numbers that we toss together. Tensors actually have real geometrical meaning. And if we just think of tensors as these multi-dimensional arrays, we sort of miss out on the geometrical meaning behind them. So if we casually toss the word tensor around to mean a multi-dimensional array of numbers, that's sort of fine. There's nothing wrong with that. But if we're thinking seriously like mathematicians and we want to understand geometry, this definition, the array definition, is simply just wrong. So it's no good to us. Okay, so let's try again. So here's another attempt at a definition. I'll just read it. A tensor is an object that is invariant under a change of coordinates and has components that change in a special predictable way under a change of coordinates. Okay, so that's certainly a mouthful. So what does that mean? So let's start with the top part. What does it mean to be invariant under a change of coordinates? Well, to explain that, I'd like you to try picking up a pencil and point the pencil toward the nearest door that you can see. So there are a few things that we can say about this pencil that are just facts, and they don't depend on any coordinate system. So for example, the length of the pencil, the length won't depend on our choice of coordinate system. The length is an intrinsic or invariant quantity. Also, this pencil is pointing toward the door.
So for example, if we are talking about the length in centimeters or meters, it will be the same overall length, but normalized to the measuring units that we use. If it will be 20 centimeters, it will be 0.2 meters. But again, it is not something that will change. It will change like in a relation to the unit of measure.
And that's just a fact. It doesn't depend on what coordinate system we use. The pencil's orientation is intrinsic or invariant.
Meaning, and the orientation, we can look about where it's like back side and where it's front side, and where does it point to?
Under the choice of coordinate system. Now the second part, what does it mean for components to transform predictably under a change of coordinates? Well, to start off, let's introduce a coordinate system here. So we have a nice 3D coordinate system with 3 vectors here that give us the main coordinate directions. And what we can do is we can measure the pencil using this coordinate system. All right, so it looks like this pencil is made up of 2 yellow arrows, 1 green arrow, and then 2 blue arrows. All right, so we can write this pencil as a linear combination of the coordinate vectors here.
It's about,
okay, so
in
what
3D
we just did
space,
here by breaking down the pencil into the coordinate vectors vectors is we measured the pencil's components. The components are just the amount of each coordinate vector that we need to construct the pencil, right? So with this coordinate system, the components are 2, 1, 2. Now, I introduced this coordinate system here, and you might think it's a pretty sensible coordinate system because all the direction vectors are the same length and they're all perpendicular to each other, so that's kind of nice. But really, there's nothing special about this coordinate system, right? I could just as easily introduce another coordinate system like this, where the vectors are all different lengths and they all sit at weird angles relative to each other. But mathematically, neither of these is more correct than another. They're simply just different choices. And so with this second coordinate system, I can sort of do the same thing. I can measure the pencil along each coordinate vector, and I can see that this pencil is made up of 2 black vectors, 3 purple vectors, and then 1 red vector. And again, I can write the pencil as a linear combination of these vectors, and I get the components 1, 3, 2.
So regarding linear algebra, both the blue, green, yellow way of describing vectors and the red, purple, black way, those are both bases to R3, and every 3D object we can describe by this way or by this way. And they have different representations because those are different vectors, but it is meaning the same pencil.
So you'll notice when I measure the pencil using different coordinate systems, I actually get different components, right? And this is a really important idea. The pencil's components are not invariant, right? They change depending on the coordinate system they use. Okay, so the pencil is invariant, but the coordinates are not invariant. Okay, that's a very important idea. So now it turns out that if we know how to change one coordinate system into another coordinate system, right? So if we know how to go back and forth between these two coordinate systems, then we should also be able to figure out how to change back and forth between these different sets of components. And this process of going back and forth between coordinate systems and components, that's what I'm going to call forward and backward transformations. And I'm going to talk about those in the next video. All right, so backing up,
Put
what a
some
tensor
timer
is,
in order
a
to
tensor is
do
an
a
object that
break
is invariant.
in a
It doesn't
15
depend on the
minutes.
coordinate system, but its components, which do depend on the coordinate system, change in some special predictable way that we can figure out using these forward and backward transformations. And this is what I'm going to call the coordinate definition of a tensor. And this definition is actually pretty good. It does get to what the heart of a tensor is. It's an object that's invariant, but whose components change. But it turns out that we can come up with an even better definition. And so I'm going to switch to that one here. So here's our third final definition. I'm just going to read it off. A tensor is a collection of vectors and covectors combined together using the tensor product. So this definition ends up being really nice. It's really short and sweet. There's just one problem. If you've never studied tensors before, you may have heard of vectors, but you've probably never heard of a covector, and you've probably never heard of the tensor product. So the downside of this definition is that we need to put in a little bit of work before we can even understand what it means. But once we understand what all these things mean, it's actually a really simple definition. Tensors are just vectors and covectors combined together in different ways using this thing called the tensor product. So this is what I call the abstract. You may have definition. Here's our third final definition. I'm just going to read it off. A tensor is a collection of vectors and covectors combined together using the tensor product. So this definition ends up being really nice. It's really short and sweet. There's just one problem. If you've never studied tensors before, you may have heard of vectors, but you've probably never heard of a covector, and you've probably never heard of the tensor product. So the downside of this definition is that we need to put in a little bit of work before we can even understand what it means. But once we understand what all these things mean, it's actually a really simple definition. Tensors are just vectors and covectors combined together in different ways using this thing called the tensor product. So this is what I call the abstract definition of a tensor. So this is really the best definition of a tensor we can come up with, and I'll get to this definition later on in the video series once we have the basics down. All right, and I have a little bonus part here. So for those who do have a calculus background, I'm going to talk about how tensors pop up in calculus, and that's when we see tensors as partial derivatives and gradients that transform with the Jacobian matrix. So you can skip this section if you aren't feeling very strong with your calculus skills. It's an extremely interesting use of tensors, and it's very important for the curved geometry we might see in general relativity. But if you're not comfortable with calculus, you can feel free to skip over this part. All right, so this is sort of the end of the introduction. I spent the last 2 weeks. I'm actually going to start transformations, so I will see you in the next one. Welcome to this first real video.
So as of now, we saw like 3 ways to describe the tensors. So the first one would be like some sort of multi-dimensional array. We can look at a number, which is a scalar, like a vector of size 1. We can look at a vector, which is an array of numbers. We can look at a matrix, which is 2D. We can look at like some sort of cube, which have 3 ways of movement inside it, like a 3D tensor, and tensor of what does he say? Rank 3, size 3. I need to look it up, and then let's go back to the video.
All right, so welcome to this as a lint fact. So what does that
An
mean?
object that is invariant under change of coordinates. So, okay, the vectors themselves, vector, which is a rank 1 tensor, they are invariant under a change of coordinates. The vector itself is invariant. The coordinates are changing, but they are meaning the same object in, let's say, real life, in the case of the pencil. And if we look at the third definition, so tensor, a collection of vectors and covectors combined together using the tensor product. So it would be something more difficult to explain, and we will see soon how do we define the covectors using linear algebra, and what is a tensor product. This is also something from calculus. As we can look at, if we look at calculus in 1 dimension, so we can think about functions that have a derivative. We can look at the derivative, and let's say our functions are behaving nicely. We can use the derivation infinite times. This is called in mathematics C infinity, where C1 is like you can use the derivative on the function, and the resulting derivative will be a continuous function. And ck, it's the same, but doing it k times. After k times of doing after you differentiate the function, the resulting function would be continuous. And C infinity, meaning you can do it infinite times, we can say it's smooth. So for let's say for simplicity, we will use smooth functions, and then we can talk about just taking derivative, and the resulting would be smooth and nice. And also, if we look at multivariable calculus, so the function, the result can move in a few directions. So in this case, we will talk about partial derivative, meaning how the function changes along each one of the axis of movement. So if we look at something like, for example, something like some sort of fabric, and we can, for example, putting it above the floor, we can look at each, as long as there are not points that intersect each other like this, we can put it above the floor, and then using each point as what is the height of the point. So each xy will be sent into a new xyz. No, sorry, the same xy with the height z. So it's the function would take xy and output z, and the graph of the function would be the image of this shirt. So there is a definition, a distinction between a function and the graph of the function. Maybe we can explain this later.
And gradients. Interesting. Next video, I'm actually going to start doing. Welcome to
Okay,
this
let's look at the
real
first one.
video in my series on tensors. The previous two videos were mostly on giving motivation and background on tensors. In this video, we're going to get started doing some actual real math. So the first thing we're going to learn is forward and backward transformations. These are the rules that let us move back and forth between different coordinate systems. I mentioned in the previous videos that tensors are invariant under a coordinate system change. So understanding how to move back and forth between coordinate systems is going to be really important for understanding tensors. Okay, so let's start off with the forward transformation. So I have two two-dimensional coordinate systems here. The old basis E1 and E2, and the new basis E1 tilde and E2 tilde. So remember from linear algebra that the word basis just means a set of vectors that give us the main coordinate directions for our space. So we have the old and new coordinate systems, or the old and new basis. So the forward transformation will move us from the old basis.
So in linear algebra, a basis is a collection of vectors that are that we can describe each point in the vector space as a linear combination of them, and that in some sort they are minimal, meaning we cannot take out one of them and still describe each point in the vector space as a linear combination. So they are both spanning the vector space, but they are minimal in their amount.
To the new basis. So how does that work? Well, all we need to do is build the new basis vectors out of the old basis vectors. So let's start with E1 tilde here. How do we build E1 tilde out of E1 and E2? Well, it looks like we need two E1 vectors and one E2 vector. So I'll just write that in here. Now, what about E2 tilde? So it looks like we need 1/2 of E1, but it's in the opposite direction, so that's actually minus 1/2. And then we need 1/4 of E2. So I'll just write those in. All right, so what we've done is we've written out the new basis vectors as linear combinations of the old basis vectors. And if I wanted to, I could write these four numbers in a 2 by 2 matrix called F. F for forward. Now,
So look at it this way. This is E1 in the terms of E1 tilde in terms of E1 and E2. And this is E2 tilde in terms of E1 and E2. And this is the change of coordinates matrix between the basis E1, E2 to the basis E1 tilde, E2 tilde.
you'll notice that the numbers in this matrix are not arranged in the exact same way as the numbers in the equations. The arrangement is flipped about the main diagonal. The reason for this is that in this video series, we are going to arrange basis vectors as rows that multiply matrices from the left. So if you remember matrix multiplication, you'll notice that this row times this column gives first entry times first entry plus second entry times second entry. And this results in our first equation for E1 tilde. Applying the same procedure for this row times the other column gives our second equation for E2 tilde. So for this series, keep in mind that when we write equations to change basis in matrix form, basis vectors are written in a row multiplied from the left. And that means that the numbers in the forward matrix are flipped about the diagonal compared to the equations. And so that's really it. That's the entire forward transformation. If we know the matrix F, then we know everything we need to construct the new basis from the old basis. Okay, so what about backward transformations? As you'd expect, it's basically just the same thing, but in reverse. So we build the old basis vectors using the new basis vectors. So how do we build E1 using E1 tilde and E2 tilde? It's a little more confusing this time, but it looks like we need a quarter of E1 tilde and exactly 1 of E2 tilde, but facing the opposite direction, so it's actually minus 1. So I'll just write those in. And what about E2? It looks like we need a half of E1 tilde plus 2 E2 tildes. And again, we can store these numbers in a 2 by 2 matrix called B, B for backward. And that's the backward transformation. So if we know the matrix B, we know everything we need to construct the old basis from the new basis. Now you might be thinking, here we have the matrix F, and here we have the matrix B. Are these really two different things? They kind of do the same job, but in opposite directions. So are they really so different? Well, let's see what happens when we multiply them. So this might actually be a good exercise for you to review matrix multiplication. To multiply two matrices, we write them like this, and to get this entry of the resulting matrix, we take the inner product of this row and this column. So in this case, it's 2 times a quarter plus negative a half times negative 1. So that's just a half plus a half, which equals 1. So I'm going to let you do the other 3 entries. But what you'll find is you get this matrix here with 1s along the main diagonal and 0s everywhere else. And this is, of course, the identity matrix.
And why is that? Because if we start, for example, with the old basis, we push forward into describing it with the new basis, and then we transfer back from the new basis to the old basis, then we go back into the old basis. So because we start with the old basis and we go back to the old basis, it's the same as, let's say, in normal numbers, we multiply by 1, it's the same number. So in linear algebra, if we multiply by the identity matrix, it will give us the same matrix that we started with.
So what this really means is that f and b are inverses. Or another way of saying that is b equals f inverse. So why?
And in linear algebra, if two matrices, meaning the same size and everything, but two matrices, their multiplication is the identity matrix. So what we know from that is they are both of full rank, meaning if it's, for example, 3 by 3 matrix, they will be of rank 3, meaning all the three vectors are not linearly dependent on each other, and that they are like one, it's in some way the opposite of the other one, where we say the inverse matrix, we mean this matrix that if we multiply by the original one, we get to the identity.
Am I using?
Just like, for example, in numbers, we have like 7 and 1 over 7. So 7 times 1 over 7 would be 1. So in here in linear algebra, the matrix times its inverse would be the identity with the respect to the size of the matrix. So the identity 2 by 2 would be this one. The identity 1 by 1 would be just a matrix where we put 1 inside. And the identity in 10 by 10 would be a 10 by 10 matrix where we have just ones in the diagonal.
Two different letters here. Why use f and b when I could just use f and f inverse? Well, just visually, I personally find it easier to tell the difference between f and b than between f and f with a tiny little negative 1.
I agree with him here.
So even though b is equal to f inverse, I'm just going to keep writing b. Okay, so that was an example in 2 dimensions. What if we want to generalize this to n dimensions? Well, it's basically the same process. We have n old basis vectors, e1, e2, all the way up to en.
So we just use f11, f12
e1 tilde,
to f1n.
e2 tilde, all the way up until en tilde.
Yeah.
And we need to decide how to build these new basis vectors out of the old basis vectors. And we do that just by choosing the right coefficients, so that all of these linear combinations work out properly. And again, we can write these coefficients in a matrix. This time it would be an n by n matrix instead of a 2 by 2 matrix. And that's our matrix F. Now, writing out all these equations is kind of annoying, so let's see if we can find a better way to write this. So if I wanted to build the ei tilde vector out of the ej vectors, what I would want to do is write ei tilde as some sort of combination of the ej basis vectors. But I still need to decide on the coefficients. So what would these be? Well, if you look up here,
what we can do regarding the combinations is, for example, let's look at ej. It's fi. It's the sum from j equals 1 until j equals n of fj and fji. Because look, let's look at e where I equals 2. It's f12, f22, f32, and so on and so forth. So we see that this I would be the second index of f, and the first index of f would be the j, something that runs from left to right.
Here you'll see that f12 tells us how much of
which
E1
is the column
makes up E2 tilde. And over here, fn1 tells us how much of En is inside E1 tilde. So really, the coefficient I want here is FJI. FJI tells us how much of EJ makes up EI tilde. So really, this summation summarizes all of the above equations nice and simply. So this is the forward transformation in n dimensions. Now for the backward transformations, I can do the same thing. We just write out all the old basis vectors as linear combinations of the new basis vectors. And we can write these coefficients in an n by n matrix called B. And we can summarize all these equations where EI is equal to the sum of EJ tildes with the coefficients being BJI. So that's the backward transformation in n dimensions. It's worth noting that with these summation formulas, we're free to relabel the summation index letters without changing the meaning of the formula, as long as we relabel the index letters consistently. For example, I can replace the summation index j with the summation index q, and the formula's meaning stays the same. We're also able to flip the order of the factors in the summation, since these are just numerical coefficients, and it doesn't matter if we put the numbers in front or in behind.
Great.
Okay, so we have the forward and backward transformations. Now, can we prove once again that they are inverses? Well, I'll start with the backward transformation just here, and if you'll notice, the forward transformation gives us an equation for EJ tilde. So I'm just going to substitute that in for EJ tilde here, and we get this. And rearranging some of the summation signs, we get this. Okay, so let's just put this on a new slide here. So looking at the formula, what's going on here is that we're building the old basis vectors using a summation of the old basis vectors. And what we need to do is, we need to decide what this middle part of the equation should be. So why don't you pause the video and take a few seconds to think about what the middle part should be.
So let's look at it. FKJ times BJI. Times J. So it would be FK1 times B1I plus again. So we can look at it as the vector of row Fk and the vector of column B Bi, and look at the scalar multiplication of them, it would be this thing. And if what we said was correct, then we look at EI and we want to describe it using the same basis vectors. All of the basis elements there is only one way of describe a vector using a basis. So EI can be represented only by 1 times EI. So what would this thing be from this way of thinking? So we must get in the end, we must get that EI is like 0 times E, let's say it's E5. So it's 0 E1, 0 E2, 0 E3, 0 E4, 1 times E5, 0 times E6, and so on and so forth. So if we say it in like mathematical kind of way, this would be the delta of Kronecker. It would be 0 if I and K are not the same, sorry, if I and k are not the same, and it would be 1 if I and k are the same. Yeah.
If we want these equations to make sense. Okay, so what we really want at the end of the day is for E1 to equal E1, and we want E2 to equal E2, and so on and so forth. We don't want any extra basis vectors in here being added because that wouldn't make any sense. So what we really want is for this middle part to be 1 when I is equal to k, and we want it to be 0 when I is not equal to k, right? That makes sense. And really, if you think about this as a matrix where I gives you the row and k gives you the column, putting 1 where I equals k means having 1s where the row is equal to the column. So we get 1s along the main diagonal here, and then we just get 0s everywhere else. So again, 1s along the diagonal and 0s everywhere else. Once again, we showed that multiplying f by b gives us the identity matrix. So f and b are inverses of each other. Now, this behavior where we have 1 where I equals k and 0 where I does not equal k, this behavior ends up being so common that we give it its own symbol, called the Kronecker delta.
Mm-hmm.
So whenever you see the Kronecker delta, just think of this relationship right here. It's a bit like telling you what the entries of the identity matrix are, where we have 1 where the row is equal to the column and 0 everywhere else. Okay, so to sum up what we learned in this video, we learned the formulas for the forward and backward transformations in n dimensions, and we also showed that the forward and backward transformations are inverses of each other, because when we multiply the f and b matrices, we get the identity matrix by the Kronecker delta symbol here. In the next video, we're going to look at vector components, which allow us to build generic vectors out of basis vectors, where the components are normally written as columns. The forward and backward matrices will transform the columns like this. Welcome back to the video series on tensors.
Okay.
In the last video, we covered forward and backward transformation.
Let's make a stop. And let's look at a little talk with Gemini. I use Gemini as some kind of tutor in order to go over the lectures and strengthen my understanding. So the question, to ensure that the actual physical vector v remains exactly the same, how must the components of this vector transform? Specifically, what is the algebraic relationship between the matrix that transform the components and our basis transformation matrix F? So my answer was F need to transform the components of the appropriate E tilde way, and this transformation matrix F coordinates are describing how to transform E1 and E2 and so on. Each column in this F describing the new linear combo that describe EJ, where EJ is the column index, but in the new basis vectors E tilde. So Gemini says, you have a good grasp of what F does to the basis vectors. It gives us exact linear combinations needed to relate the old basis E to the new basis E tilde. Now let's focus on the components of a specific vector V to answer the original question. Imagine a physical arrow drawn on a piece of paper. This is our vector V. Suppose our forward transformation F simply scales our basis vectors so that the new basis vectors are exactly twice as long as the old ones. If the basis vectors get twice as long, what must mathematically happen to the numerical components of V so that the physical arrow on paper doesn't change its length and direction? Based on that intuition, what is the exact algebraic relation between the matrix F and the matrix that transform the components? So let's see. Let's say we are from centimeters to meters. Okay. So if my height is like 170 centimeters, then in meters it would be 1.7 meters. And now let's say we are from the opposite, from meters to centimeters. So no, sorry, from we are getting longer. So from centimeters to meters. So in this way, we are making the unit of measure bigger, and thus the amount of steps need to be smaller. Yes, if I need to jump and my jumps get bigger, then the amount of jumps is smaller in order to get where I want to. So every basis vectors would be twice as long. So the transformation matrix would be just 0.5 times the identity matrix, meaning it would be each one of the columns would be 0.5 and not 1. Each one of the elements on the diagonal. This is because the units got bigger, so our way of describing a vector needs to take in account smaller steps. Specifically, if we take steps that are twice as big, we need to take half of the steps. And of course, it doesn't need to be like a whole number. It can be fractionally half of the steps. Let's see, Gemini spot on, your intuition is exactly right, because the steps, the basis vectors, are twice as big. You only need half as many of them to reach the exact same physical destination. Mathematically, this means that if your basis vectors transform according to a matrix F, the forward transformation, the components of your vector must transform according to the inverse. f to the minus 1, we call it b, like backwards. Because the components transform in the opposite way to the basis vectors, we say these components are contravariant. This means if we are making one bigger, the other one gets smaller. This is fundamental property of the standard vectors you are used to working with. So let's see a Feynman technique. Now it's time to synthesize this before we move to the next video. Imagine you are at a whiteboard in front of your high school math students. They know about basic coordinate planes and matrices, but they are used of thinking of a vector purely as a fixed columns of numbers, 2 and 3. How would you explain them, the difference between a physical geometric vector and its components, and why those components must change backwards when we stretch or rotate our underlying coordinate grid? Write out your explanation for them. So I say a physical geometric vector in the example is a line in 2D space. Now we want to keep this line. The components tell me how to draw it according to a chosen basis. We usually take the 1 and 0 and 0, 1 basis in R2, but we can do it in many ways as long as the two vectors are not linearly dependent. Thus, if we change our way of describing the vector, the translation between ways of describing the vector needs to take in account the change. The physical vector would stay the same. The components, the way of describing the vector in the space must change. And if we, for example, make our steps 3 times larger, then the amount of steps would need to be third of the original amount. So the relation between the old vectors and the new vectors is the opposite of the translation matrix from the old base to the new base. Okay, let's see if it's something that Mr. Gemini is okay with. Then we can continue. Okay, so F would be the transformation matrix or change of basis matrix. By the way, there is a nice technique that if we want from, let's say, arbitrary base 1 and the arbitrary base 2, so we can think of the change of basis matrix as two change of basis matrices. One is from taking this arbitrary basis and going into uh, the most well-known base, which is, you know, 1 and then zeros, 0, 1 and then zeros, and so on, which is, you know, the standard base, as we say. And from then we can translate again to the other arbitrary base, and it would be more easy this way. We have 5 more minutes to this session. I'll make it a little longer. Okay. Make it a little longer. We need to look at functionals. Okay.
The vector. So what is a vector exactly? Much like tensors, you might get different answers to that question depending on who you ask. So this is one definition you might hear. A vector is a list of numbers, or a vector is a one-dimensional array of numbers. So that's a nice, easy definition. And here are a couple examples of vectors, v and w, and they're just lists of numbers. So you probably already know, if we want to add these lists together, we just add them like this, right? We just add the corresponding elements to get the new vector with elements v1 plus w1, v2 plus w2, and so on and so forth. So that's vector addition with lists. And you probably also know that we can scale vectors using a scaling constant like this. So we just take the scaling number a and give it to each number inside the list and multiply each number inside by a. So this definition of a vector is easy enough, but there is a problem. And the problem is that these list of numbers are actually vector components, not the vectors themselves. So if you'll recall, I said before that vectors are invariant under a change of coordinates, whereas vector components are not invariant under a change of coordinates. So it's really important to remember that a vector and a vector's components are really, really not the same thing, and we should never confuse the two. So much like saying that a tensor is a multi-dimensional array of numbers, saying that a vector is just a list of numbers really misses the geometrical truth that lies behind the numbers in the list, right? Because vectors are geometrical objects that have geometrical meaning. So this definition isn't really very good. So let's try again, definition number 2. A vector is like an arrow, just like an arrow floating in space. So this is a more geometric answer. We can draw arrows, and we don't really need to refer to a coordinate system in order to understand them. And just like before, we can add vectors together. To do this geometrically, we just place the tail of the second vector on the tip of the first vector, like this. Some people call this tip-to-tail addition. And the resulting vector is just the vector that goes from the initial point on the first vector to the final point on the second vector. Another way of thinking about this is that we are creating a parallelogram using the vectors v and w, and the addition of v and w is just the vector that points to the opposite corner of the parallelogram. Yeah. So that's vector addition under the arrow interpretation of vectors. And also, just like before, we can scale vectors. So if we take the vector w and scale it by 2, we would just get a new vector that points in the same direction but is twice as long. And again, we can do that with any other number like 5 or 3/4 or pi or whatever number we choose. Also, if we have some vector v and we scale it by -1, that means that we keep the vector length the same and just reverse the direction like this. So that's vector scaling under the arrow interpretation. So the arrow interpretation is pretty good. It makes it really easy to draw pictures and visualize vectors. You'll notice I've been using this interpretation all throughout the video series so far, and I plan on continuing to do that. But there is a problem here,
kind of
and that problem is that not all
molten
vectors can be visualized as arrows.
rubber on
So
the
unless you've studied a bunch of
mouse.
linear algebra, this might actually be a bit surprising to you, because a lot of teachers just teach vectors as if they are arrows floating in space like this. So these arrow type vectors are actually just a special kind of vector called a Euclidean vector. But there are other types of vectors out there that can look pretty different. I'm going to leave that until another video to explain what I mean, but for now, just remember that not all vectors are Euclidean vectors. Okay, so let's try one last time. And this definition says that a vector is a member of a vector space. So what is a vector space? So a vector space is a collection of four things. The first thing is a set of vectors V, which are the vectors themselves. The second thing, S, is a set of scalars. So these are the things that we use to make vectors bigger and smaller. The third thing is some sort of addition rule that lets us combine two vectors together. So we could add, say, a vector V and a vector W and get some new vector V plus W like this. And the fourth thing is some sort of scaling rule, which I'm denoting as dot. And that lets us use scalars on vectors to change their size. Usually, instead of writing a dot, I just write the scalar right next to the vector, but you could put the dot there if you really wanted to. So really, what all this means is that vectors are things that we can add together using the plus addition rule, and that we can scale using the dot rule and a scalar. So this is a pretty abstract definition.
Also, this plus and multiplication rules are not exactly the normal plus and multiply rules that we know from numbers, so we need to take that in account. This is a bit more abstract than that, so I am sure he will make the distinction, but I also wanted to point that.
There's no numbers that we can do number crunching with, and there's no pictures that we can draw. All we really have at the end of the day are a bunch of rules. So even though it's abstract, the reason this definition is so great is that there are a ton of things in math that can be added together and scaled. And even if we can't draw them as arrows, we can still apply vector rules to them. So if this definition seems a bit strange to you, I wouldn't worry about it much for now. I think it will make more sense in the future. For this video and many videos later on, we're just going to stick with Euclidean vectors since they're easy to draw pictures with and easy to visualize in our heads. So now that we have some idea of what a vector is, let's talk about how vectors behave under a change of coordinates. So you might remember from the previous video, I had two coordinate systems, the old basis and the new basis, and we figured out the forward and backward transformations that let us move between them. So let's say we have a vector V sitting here in this space, and we want to figure out the vector's components. Well,
Yes,
since we have two different coordinate systems, we can measure V using two different bases. So let's start with the old basis E1, E2. How can we write V as a linear combination of E1 and E2? Well, it looks like we need one copy of E1 and 1.5 copies of E2. So I can write this out, V equals 1 E1 plus 1.5 E2. Now let's do the same thing in the new basis. So it looks like we use 1 E1 tilde and 2 E2 tildes. So V equals 1 E1 tilde plus 2 E2 tilde. And because I have the components now, I can write V as a column vector. So in the old basis, the components are 1, 1.5, and I've put a little EI down here to remind us that we're measuring in the old basis. And in the new basis, the components are 1, 2. And again, I've put a little EI tilde here to remind us that we're measuring in the new basis.
Mm-hmm.
All right, so how are these two sets of components related to each other? Okay, let's think about that. Remember, with the old and new basis, the forward transformation f brings us from the old basis to the new basis, and the backward transformation b brings us from the new basis to the old basis. Now maybe that works with the components too, right? So let's try applying the forward matrix f to the old basis components and see what we get. Okay, so that's not right. So what happened here? Did we do the math wrong? Like, what's up? So this might sound crazy, but I'm going to suggest that we try using the backward transformation on the old coordinates instead. So let's give that a try. Okay, so by applying the backward transformation on the old components, we ended up with the new components. So for basis vectors, forward brings us from old to new and backward brings us from new to old. But with vector components, it's the opposite. Forward brings us from new to old and backward brings us from old to new. So what's up with that? Right? This might seem really weird at first, but it actually makes complete and total sense. And I would actually be a little bit worried if this wasn't true. So to understand why this happens, you'll have to check out the next video. So in the previous video, I left off with this mystery of why vector components transform in the opposite way compared to our old and new bases. And I said that this makes a lot of sense. So let's talk about why that is. So here I have an old basis, E1, E2, and I have a vector V living in this space. And the components of V look like they're about 1, 1 in the old basis. Now what would happen if I increase the size of the basis vectors by a factor of 2? So I make them twice as big. Right, so what if I said E1 tilde and so what are the components of V in the new basis? Well, it looks like they're about 1/2, 1/2. So while the basis vectors grew by a factor of 2, the vector components shrunk by a factor of 2, right? They did the opposite thing. And this makes a lot of sense because even though V doesn't change, right? V is invariant. V looks smaller when we measure it using the new basis vectors because the basis vectors, the measuring sticks that we're using, got twice as big. All right, so here's another example. Again, we have the old basis E1 and E2 and the vector V, and just notice that V is made up of about equal parts E1 and E2. So the angle V makes with E1 is about the same as the angle that V makes with E2. And this means that the components in each direction are about the same. Now, what would happen if we rotated the basis clockwise? Okay, so the new basis would look something like this, right? Now, what about the components of V? Well, if you look at the angles, the angle V makes with E1 tilde is actually bigger than the angle V makes with E2 tilde. So again, V is invariant, it hasn't moved, but now it's leaning closer to E2 tilde compared to E1 tilde. And that makes it feel like it's rotating counterclockwise because the angle it makes with the second basis vector got smaller. Okay, so again, the components did the opposite thing. The basis rotated clockwise and the components rotated counterclockwise. So going back to this diagram, when vector components behave the opposite way that basis vectors do, that actually makes perfect sense. When the basis gets bigger, the components will shrink. When the basis rotates one way, the components will rotate the other way. Whatever the basis does, the components do the opposite. So now we have some intuition as to why this sort of opposite behavior happens in 2D. Let's see if we can prove it in any dimension. So let's just recall that we have two ways of writing V. We can write it as a linear combination of the old basis vectors with the coefficients being the old components, or we can write it as a linear combination of the new basis vectors with the coefficients being the new components. And we can also write these as summations just to save some space. All right, so both of these summations are equal to B. Now let's bring out our forward and backward transformations here. So if we take the old basis and old components, what we can do is we can use the backward transformation to replace the old basis vectors with the new basis vectors. And so we get that, and rearranging the summations, we get this. So now we have V written as a summation of the new basis vectors. So what's this part in the middle? Well, if you look up here, when we write v as a summation of new basis vectors, the coefficients have to be the new components v tilde. So this here is equal to v tilde. So we've proven here that to move from the old components to the new components, we actually use the backward transformation, which is what we expected. And the same is true in the other direction. We can start with the new components and basis vectors, then replace the new basis vectors, go from the new transformation.
Good reminder
we know how
from
the basis
linear
vectors
algebra.
transform, and we know how vector components transform, which is in the opposite way. Now, because vector components behave contrary to the basis vectors, we say that vector components are contravariant.
Components
and we'll see later that vectors are contravariant tensors. So I'll talk more about what that means later. One last thing I'm going to mention. So here you can see we've written the vector v as linear combinations of the old and new basis. But these vector components, since they are contravariant, we're going to make a small change in the way we write them. What we're going to do is, instead of writing these little I indices below the v, we're going to switch that up, and we're going to write the indices above the v instead. And this reminds us that the components are contravariant. Okay, since the basis indices are at the bottom and the vector component indices are on top, it's sort of a reminder that they behave in opposite ways. Now, you might be a bit worried that you'll confuse these upper indices with exponents, right? Because exponents sort of look the same. But exponents pop up so rarely when we're dealing with tensors that you can basically always assume that these are vector indices and never exponents. All right, so that finishes up our discussion of vectors. In the next few videos, we're going to talk about covectors, which are another example of a tensor. In the last couple of videos, we saw our first example of a tensor.
What we saw for now was the explanation of tensors and a little bit of linear algebra, ways of presenting vectors in many kinds of bases, and the transformation from one base to the other base, and that the coordinates of a given vector are changing in the other direction. So, for example, if we change from base E1 to base E2 by a change of matrix F, then the coordinates change by the inverse of the matrix, by the B. Okay, so far it was a good chunk of learning. Now I will mute the mic and close the. Maybe I can see what we can do with the camera. I see it's not something that we can close easily for now. So okay, maybe I can put something on the camera. I will put something on the camera, and we will be back in about 10 minutes. For now, what we can do is I will stream a timer. Just a second. So this is the timer. I will be back soon. So I have 1 more minute for the break. Time to look at WhatsApp a little bit. All right. I will just need a few more seconds. Okay. We'll reset the clock. Maybe I can share the whole screen. Or maybe about privacy. So we can look at the videos. Okay, covectors.
Which was the vector. And we saw that vector components transformed in the opposite way that basis vectors do. And because of that, we said that vectors were contravariant. In the next few videos, we're going to talk about our second example of a tensor, which is the covector. So the first thing we're going to do is we're going to answer the question, what is a covector? Well, as a starting point, we can think of covectors as basically like being row vectors. And you might think, well, row vectors aren't too hard. A row vector is just like a column vector that we take and flip on its side like this, right? Well, it's not quite that simple. You might not be aware of this, but column vectors and row vectors are fundamentally different types of objects. And the reason you might think that they're basically the same is that you've normally been dealing with them in an orthonormal basis, which is a basis where all the vectors are 1 unit long and they're all perpendicular to each other. So when we're dealing with an orthonormal basis, the idea of flipping column vectors onto the side to get row vectors is actually true. But it's not true in any other coordinate system. And to realize why, we're going to have to think about row vectors as functions. So we can think of a row vector as a function on a column vector. So in this example, this row vector 2, 1 would be the function, and this column vector 3, -4 would be the function's input. To find the output value of the function, we just do the standard matrix multiplication or dot product of this row and column vector. So carrying that out, we get 2 times 3 plus 1 times -4, and that's just 6 minus 4, and then we get the output 2. Now, if we have any general covector alpha acting on any general vector v, then we get the output value by taking the dot product of the two vectors like this, and we can write that more compactly using this summation. So ultimately, we should think of row vectors as functions that take an input from some vector space v and return a real number or a scalar. Okay, so let's examine how these row vector functions work a little bit more. Let's say that we have a row vector which is acting on two vector inputs that are added together. So there are two ways that we could go about calculating the output. One way is to distribute the row vector to each of the inputs and then add the results, and that gives us this output here. And the other way is to add the inputs together and then get the row vector to operate on
Would
the
be the
column vector
exact same
input.
thing.
And you can see that this gives us the same output, 5, as we had in the previous example. So row vectors as functions have this property here where we can add the inputs before or add the outputs after, and we'll get the same result. Another idea we can consider is what if the vector input is scaled by some number like this? And again, there are two ways that we can compute the output. We can scale the input vector and then have the row vector act on the result to get this. Or we can put the scaling number out in front and then scale the results of the row vector acting on the column vector. And again, we get the same result. So row vectors as functions have this property that we can scale the input or scale the output, and we get the same result. So to sum up, a covector is a function that takes a vector and produces a scalar or a number, and it has the property that we can add the inputs or add the outputs to get the same answer, and it has the property that we can scale the inputs or scale the outputs by the same amount and get the same answer. More generally, these two properties, when they work together, look like this. And this behavior of being able to add or scale either the inputs or the outputs and getting the same answer is called linearity. So covectors are linear functions. So now, how do we visualize these covectors? We know that we can visualize ordinary vectors as arrows like this. And we sort of could do the same thing with covectors, but that's sort of an awkward thing to do for visualizing a function. And it turns out there's a much better way to do it. So let's start by thinking of this 2D row vector as being a function on two variables, x and y. So the row vector 2, 1 can really be thought of as a function 2x plus 1y. So how can we visualize a function of two variables that produces one output? Well, this is very similar to a problem that map makers have to deal with when they want to convey elevation on a two-dimensional sheet of paper, right? When you have a topographic map, you basically need to show off the slopes of mountains and valleys, but only using a 2D page. So what topographers do is they take a map and they draw curves of constant elevation, like this. So this curve here that's labeled 3,000, everywhere on this curve is exactly 3,000 feet high. And this curve over here labeled 2,000, everywhere on this curve is 2,000 feet in elevation. So just looking at this map here, we know that when the lines are stacked together really, really densely, like over here, this is a place where the elevation changes really, really steeply, right? Whereas over here, where the lines are less dense, this is a comparatively shallow slope because the elevation changes less quickly. Another way of thinking about this is that if we have this red mountain here, if we take a horizontal slice at some height, we'll end up with contours that look different, right? So if we slice at this elevation, we'll get this contour. If we slice at this elevation, we get this contour. And this elevation is this contour. And these would be like the curves of constant height on a topographic map. So let's take this idea and apply it to the row vector 2, 1, which again, when taken as a function of inputs x and y, gives us the value 2x plus 1y. So to start, let's ask, where does this function equal 0? Well, if we change this around a little bit, we get the line y equals minus 2x. And that would be a line like this. And next we'll do where the function equals 1, so we get y equals negative 2x plus 1. And that would be a line with the same slope, but just shifted up a little bit. And when the function equals 2, we'll get another line just shifted up by 2 units instead. And so when this function equals negative 1, we'll get the same line just shifted down. And when the function equals negative 2, same thing, just shifted down even lower. Okay, so let's clean this up. So this is our covector 2, 1, visualized as stacks of lines. And note that since the stack is increasing toward the upper right, we can add these little arrows here to remind us of the direction of increase, right? This stack has a direction. It's increasing this way and decreasing the other way. And you'll notice that if I were to draw the vector 2, 1 as an arrow here, the arrow would be perpendicular to all the lines in the stack. All right, so we can visualize covectors as stacks of lines, and this ends up being really, really useful, and I'll show you why on the next slide. Okay, so here I have the same covector alpha over and over again, visualized as a bunch of directed stacks, and over this covector I have the vector v in yellow pointing in different directions. And what I'd like to do is I'd like to figure out the numerical value of the covector alpha acting on the vector v. So let's take a look at this first one here. So remember, each line in the stack is a line of constant value. So to get the value of alpha acting on v, all I need to do is count the number of lines that v pierces. So here v pierces 1, 2 lines. So the value of alpha of v would be 2. Okay, in this one, it doesn't pierce any lines, but it gets halfway to the first one, so we would say 0.5 or 1/2. Here it pierces 1, 2, 3 lines, but it's going against the orientation of alpha, so that means that alpha of v is negative 3. And in this last example here, the vector is parallel to the stack, so we get a value of 0 since the vector doesn't pierce any lines at all. So this visualization is really nice, right? We don't need to know anything about coordinate systems or components in order to understand how a covector acts on a vector. We just look at the picture and count the number of lines the arrow pierces, and then that's the answer. Okay, so hopefully this is simple enough. Let's start thinking about ways we can modify covectors to get new covectors. So we have this covector alpha here again, and it acts on vector v to give a value of 2. Now, if I asked you to make this covector twice as big, what would you do? Right? Maybe you should pause the video for 10 seconds and think about it. Okay, so if we're looking for...
So if v would be twice as big, then the amount of lines it would intersect would be twice as big as well. So it would be 4 lines.
For a covector that's twice as big, what you might be thinking is, well, if I want the covector to be bigger, then I just spread out the lines and make the space between them nice and big, right? But actually, no. What we want to do is make the stack denser, because when we make the stack denser, it increases the value of alpha of v, right? So when we pierce alpha with v, we get 2. But when we pierce 2 alpha with v, we get 4, because there are 4 lines that are pierced. So applying 2 alpha to v is the same thing as applying alpha to v and then scaling the result by 2. Now, what if we wanted to shrink alpha to half its size? Well, you probably already know the answer. In this case, we spread the lines out so that they're half as dense. And now when we apply 1/2 alpha to v, we get a value of 1 because it only pierces 1 line. And again, that's the same thing as applying alpha to v and then scaling the result by 1/2. Okay, so that's scaling covectors. Now, what about adding them together? So here I have 2 covectors, beta and gamma. Beta of v is 3, and gamma of v is 2. Now, let's say I want to add beta and gamma together, so what would I do? Well, what we do is we create a new stack that has the same density as beta in the beta direction, and the same density as gamma in the gamma direction. Okay, so I'll show you what I mean by that. Here's the new covector beta plus gamma. And you'll notice in the beta direction, V pierces 3 lines, 1, 2, 3, and in the gamma direction, V pierces 2 lines, 1, 2, which is just what we had before. So in a sense, beta has a horizontal density of 3 and a vertical density of 0, whereas gamma has a horizontal density of 0 and a vertical density of 2. And beta plus gamma, which is both of those combined together, it has a horizontal density of 3 and a vertical density of 2. And you'll notice that the vector v actually pierces 5 lines, which is 3 plus 2. So when we add covectors like this, applying the added covector to v gives us the same result as when we apply the individual covectors and then add the results. So that's adding covectors. Okay, so what we've done here is that we've shown that covectors have sensible scaling and adding rules. And what did I say before about things that we can add and scale? What does that mean? It means that we have a vector space, right? So if we have some ordinary vector space V with the scalars and the adding rules and the scaling rules, the set of all covectors, which act on the vectors of V, form a new vector space called the dual space, which we denote by V star. And this has a different set of adding rules, which I'm calling red plus, and a different set of scaling rules, which I'm calling red dot. And the reason I'm writing these rules in different colors is because they're actually different rules, right? The black rules are for adding and scaling vectors, like we did with arrows, and the red rules are for adding and scaling covectors, like we did with the stacks of lines. Okay, so the elements of V star are covectors, which are functions that go from V to the real numbers. The new scaling rule, which is the red dot, says that we can scale a covector by some number n just by applying the covector and then scaling the result by that number n. And the addition rule red plus says that we can add covectors by applying each one to the vector and then adding the results. So I'm not going to keep writing these in red. I just wanted to be very clear that the adding and scaling rules for these two vector spaces are different. Okay, so to sum up, covectors are functions from vectors to the real numbers. These functions have the properties that we can add and scale the inputs or add and scale the outputs to get the same answer, and that's called linearity. So these are linear functions. The set of all covectors that act on a vector space V together form the vector space V star, and these covectors have their own adding and scaling rules. And finally, we can visualize covectors as oriented stacks of lines. So when a covector alpha acts on a vector V, we just count how many lines the arrow pierces to get the answer. That more or less sums up what a covector is. So we're continuing with our discussion of covectors. In this video, we're going to talk about covector components. So just a quick review, we said that covectors are functions that take vectors to produce numbers. These functions are linear and obey these properties here. These functions can be added and scaled in a meaningful way, and because of that, they form a vector space, which we called V star. And finally, we can visualize covectors as these oriented stacks of planes. So when I first introduced covectors, I said that they were a bit like row vectors. So we know that a column vector really represents a vector's components in a given basis, right? So that makes you think that row vectors somehow represent a covector's components, and that's exactly correct. So I'd just like to pause here and state this in case it's not already obvious. Covectors, like vectors, are invariant. They are purely geometric objects and they do not depend on a coordinate system. But covector components do depend on the coordinate system. So a covector will be represented by different row vectors with different components depending on which coordinate system we're using. Alright, so that aside, what do we even mean when we say that a covector has components? When we write the column vector 2, 1 in reference to a basis here, what we really mean is that this vector is given by the linear combination 2e1 plus 1e2. We're just telling you how much of each basis vector is needed to make the vector. So what are we talking about when we say a row vector 2, 1? Like 2 of what and 1 of what? So remember, covectors are functions from the vector space V to numbers. Covectors don't live in the vector space V, right? They take vectors in V as inputs. So we can't use basis vectors in V to construct covectors. So what do? Well, what we're going to do is we're going to take a basis E1, E2 for V, and we're going to introduce
Just a minute. It says that there is a problem in the description. So I open it via YouTube.
So we're continuing with
Spacing of epsilon covectors in the diagram. So wrong. The corrections. Okay, so we will when we have the this epsilon spacing, I will show it. 619 and 753. All right.
two special covectors, epsilon and epsilon 2, which are both functions from vectors to numbers. And you'll notice I put the labels 1, 2 above the covector instead of below. I did that on purpose, and we'll get to why I did that later. Anyway, these covectors are defined as follows. When epsilon 1 acts on E1, we get 1. And when epsilon 1 acts on E2, we get 0. And when epsilon 2 acts on E1, we get 0. And when epsilon 2 acts on E2, we get 1. So if that's confusing, all this really says is that if the top number matches the bottom number, we get 1. And if the numbers are different, then we get 0. So to sum all this up, we can write epsilon I of EJ is equal to the Kronecker delta IJ.
Nice.
Remember that the Kronecker delta says if I equals J, we get 1, and if not, we get 0. So right here is how we define the epsilons. So what do these covector epsilons actually look like as stacks of lines? So to find that out, let's apply them to a vector. So here's epsilon 1 acting on some vector v. And of course, we can write v as a linear combination of basis vectors e1, e2. And remember, since covectors are linear, we can add and scale the inputs or add and scale the outputs and get the same answer. So we can bring the addition and the scaling numbers outside the function like this. And epsilon 1 of E1 goes to 1, and epsilon 1 of E2 goes to 0 by definition. And so we're just left with V1. And we can do the same thing and apply epsilon 2 to V, and we end up with the second component, V2. So what these epsilons are doing is that they're projecting out vector components, right? When we apply epsilon I to V, we get the ith component of V in the E1, E2 basis. So epsilon 1 visually looks like this because it helps us get the first component of V, where E1 is the basis vector that points in this direction. And epsilon 2 looks like this because it helps us get the second component of V, where the E2 basis vector points in this direction. So that's what the epsilon covectors look like. Now let's apply some general covector alpha to V. So this could be any covector we choose. And again, let's expand V in the basis E1, E2 and use the linearity of alpha to get this. Now remember, the components of V can be obtained by applying the epsilons, right? The epsilons project out the components. So we can rewrite alpha of V like this. And what we're going to do now is we're going to make these definitions here. So we define alpha of E1 as the number alpha 1, and we define alpha of E2 as the number alpha 2. So that means we can rewrite this. And using the scaling and addition rules for covector, we can rewrite this sum as a single covector like this. And finally, we get this. So alpha is equal to alpha 1 epsilon 1 and alpha 2 epsilon 2. So what we've done is we've written a general covector alpha, which could be any covector of our choice, as a linear combination of the epsilon covectors. So what this means is that the epsilon covectors form a basis for the set of all covectors. And for that reason, we call these epsilons the dual basis, because they're a basis for the dual space V star. So we've written this out algebraically, but let's try to think of this visually so we have a better idea of what's going on. Say we have a covector alpha, a stack of lines living in a space with basis e1, e2. We can get the components of alpha by applying it to the basis vectors e1, e2. So we're just going to count the number of lines pierced here. And now, using these alphas, we can write covector alpha as a linear combination of epsilon 1 and epsilon 2 like this. So the process is, we start with our vector basis, and then using this definition here, we get the dual covector basis. And then using those, we can express any covector as a linear combination of the dual basis. But remember, these epsilons aren't the only basis we could use to express alpha. We could use any basis that we wanted. So alternatively, we could start with this vector basis, and then using this rule, we can define another dual basis, which are the epsilon tildes, which are these. And we could also express any covector as a linear.
Here is the first mistake that he said. So there would be another way of describing it regarding epsilon 1 and epsilon 2. Okay, so taking note that the picture is a mistake. I will not show the correct picture, but we can find it from the internet in the video of index 5 in the series. There is a link to Inger.
Combination of the epsilon tildes. So there are multiple bases that we can use to express a cotildes. Okay, so let's say we have a covector which is represented in the old covector basis, the epsilons, and has components 2, 1. What would those components look like in the new covector basis, the epsilon tildes? Well, all we need to do is apply alpha to the new basis vectors, e1 tilde, e2 tilde. So let's start working this out. So what's the first component? That's alpha of e1 tilde. Well, looking here, we see that e1 tilde is just 2e1 plus 1e2. And by linearity of alpha, we can do this. And we know how alpha acts on e1 and e2 from up here. These are just the components of alpha in the old basis. And this works out to be 5. And we can do the same thing for the second component. e2 tilde is negative a half e1 and a quarter e2. And we can use the linearity of alpha, and we replace these with the components in the old basis, and we get negative 3/4. So this covector alpha has components 2, 1 in the old dual basis, but it has components 5, negative 3/4 in the new dual basis. And you'll notice that the old and new covector components are related by this matrix, which is the forward matrix. So with covector components, forward brings us from old to new, and backward brings us from new to old. And this is actually the opposite of what we did for vector components under a change of basis. So this is why we can't just flip column vectors on their side to get row vectors. It works in the orthonormal basis, where we can write this yellow vector using 2 e1s and 1 e2. And coincidentally, e1 just happens to pierce 2 covector lines, whereas e2 happens to pierce 1 covector line. So the vector components and covector components are both 2, 1. But in the new basis, we only need e1 tilde to make the vector v, but e1 tilde pierces 5 covector lines. e2 tilde doesn't contribute to the vector v at all, but pierces 3/4 of the way to a covector line in the negative direction. So vector components are measured by counting how many are used in the construction of a vector, but covector components are measured by counting the number of covector lines that the basis vector pierces. In the last video, we saw that all covectors can be written as linear combinations of the dual basis vectors. We saw how covector components can be.
Okay, so far we look at covectors, and as functionals, they get a vector, and they output a number, and now they are both linear, as we saw, so they form a linear space, which is called the dual space. But the way to think about them is not just vectors that we flip. It is also, it's not always correct. So the way to think about it should be um, this intersection of imaginary lines that we saw, because this depiction is staying consistent with a change of basis when we have, for example, a basis which is not orthonormal.
Obtained by counting how many covector lines that the basis vector pierces. And we also saw that covector components transform in the opposite way that vector components do. So now we're just going to confirm what the covector transformation rules should be mathematically. So the first thing we need to get out of the way is figuring out how covectors themselves transform. So not covector components, not the alphas. We're talking about the covectors themselves, which are the epsilons. So with vectors, in order to get from the old basis to the new basis, we build the new basis vectors out of the old basis vectors, right? And that was our forward transform. Now we want to do the same thing with covectors. So how can we build the new dual basis out of the old dual basis? What are the Q coefficients that let us do this? So to figure this out, we start by applying epsilon 1 tilde to E1 and replacing epsilon 1 tilde with the epsilons as written here, and using linearity rules we can get this. So we know that this goes to 1 and this goes to 0. So epsilon tilde of E1 is equal to Q11. And if we apply epsilon 1 tilde to E2, we get that it's equal to Q12. Okay, so an alternative way of writing epsilon 1 tilde is like this, and these parts here are just numbers. Okay, so given this, let's bring out our backward transformation so that we can write out old basis vectors in terms of new basis vectors. So we get this. Now using the linearity of covectors, and these go to 1, while these go to 0. And we get this, the new dual basis vectors in terms of the old. And if you churn through all that again, you can do the same thing for epsilon 2 tilde. So you'll notice that these coefficients and these coefficients over here are awfully similar, right? So this means that to go from the old dual basis to the new dual basis, we use the backward transformation. Okay, so let's try and prove that for any dimension. Okay, so I have a ton of stuff here. I have our dual basis definitions. I have our forward and backward transformations. When we select vectors to the new basis vector ek tilde. Now the left-hand side becomes a Kronecker delta by our definition here. And on the right-hand side, we can replace the new basis vectors with a linear combination of the old ones using the forward transformation. And by linearity of covectors, we can take the summation and the scaling constants outside. And this also becomes a Kronecker delta by this definition here. Now on the right, this term here would be equal to 0 when j doesn't equal L. So we can ignore all the terms where j doesn't equal L. We only care about the terms where j equals L. So what that means is I can replace this L here with a j, since those are the only terms we care about. And so now we have that Q multiplied by F gives us the Kronecker delta. So in other words, Q and F are inverses. But remember that we already know that the inverse of F is B. So what that means is that Q is equal to B, since F can only have one inverse. So Q is equal to the backward transform. And so we move from the old dual basis to the new dual basis using the backward transform. And now you understand why we write covector indexes up top, because they transform in the opposite way that basis vectors do. So here I've summarized the basis vector and covector transformation rules, and again, they are opposites. So now that we know how basis vectors transform, figuring out how their components transform is really easy. We just write covector alpha as a sum of the old basis covectors. We use the forward transformation to rewrite the old basis in terms of the new basis. We rearrange the sums, and we see that this part in the middle has to be equal to the new covector components alpha tilde. And so we find out that the forward transform brings us from the old covector components to the new. Likewise, the backward transformation brings us from the new covector components to the old. So covector components transform in the same way that the basis vectors do. And let's do a sanity check to make sure that makes sense. So here we have a covector sitting in space with basis E1, E2. And it looks like E1 pierces 2 lines and E2 pierces 2 lines. So the components in this basis are 2, 2. Now what if we made these basis vectors twice as big? So we get a new basis here, E1 tilde, E2 tilde. And what are the covector components now? Well, E1 pierces 1, 2, 3, 4 lines, and E2 tilde pierces 4 lines as well. So the components are 4, 4. So this means that when we increase the size of the basis, we also increase the size of the covector components. So covector components transform in the same way that the basis vectors do. So hopefully that makes intuitive sense now. So here I've summarized all the transformation rules that we've learned so far in these videos. We started with the transformation rules for basis vectors, and then we figured out that the transformation rules for vector components were the opposite compared to the basis vectors. So we said that they were contravariant. Then earlier in this video, we found the transformation rules for basis covectors were also opposite compared to basis vectors. So basis covectors also transform by the contravariant rule. And finally, just now, we found that covector components transform in the same way that basis vectors do. So this means that covector components transform covariantly. And that's why we write the indices on the bottom, just like with basis vectors, because they transform in the same way. So that finishes off covectors. In the next video, we'll talk about our third example of a tensor, which is the linear map.
Okay, so for now, we have 15 minutes, 16 minutes, something like that. I will talk with Gemini a little bit. You know what? Let's share the screen. Fuck it. As you see, Hebrew, as I'm from Israel. Okay, let's look with Gemini, the thing. Okay. So when we take basis vectors to be twice as long, the amount of contour lines they pierce is twice as much, meaning the components are covariant with the basis vectors, the components of the co-vectors. Covariant is moving in the same direction, and contravariant is moving against the direction. Based on the rules established in the video, where do we place the indices? That's like I or j for the components of a standard vector, which is contravariant, versus the components of a covector, which is covariant. So the indices in standard vector are upwards, and for covariant vector are lower. This explains that upwards are contravariant to the basis, and lowered is covariant to the basis. Okay, so look at co-vectors as lines in space that differ as an error in 2D space that we can deduce a grid of lines that are parallel, that are perpendicular to this arrow and are parallel, where each one differ from the next by a space of 1. The co-vector acting on a given vector will just say to us how much does this vector as is vector. In measure of how many parallel lines it intersects, where the size of the lines, the size of the difference in the lines is just the size of the covector. Yes, so it's not a space of one, it's space of the covector size. So if we make the basis elements bigger, then the basis vectors are bigger, and the parallel lines remain the same, then we will intersect more parallel lines. So getting the basis elements bigger is like shrinking the co-vector basis elements, which says that the coordinates of the co-vectors also get bigger because they count the steps. So co-vectors are like rulers where one unit is the size of the vector and the direction of measure is the direction of the co-vector. Let's see if I was correct. If we multiply the co-vector, then the contour lines need to be more closer. So help me explain better for this question and the next one. We have 3 minutes. So the co-vector is perpendicular to the parallel lines. This means that those are all the collection of lines in space that begin where he begins and that have scalar multiplication. Scalar have inner product of 0 with it, and all of the vectors that have a given space from that but are still parallel to them, where the given space is 1 over the size of the co-vector. Right now, it's 1 over the we will take a few minutes extra. Let's make then we go back. Just a second. Okay. Null space. Okay, now we ought to take a 10 minutes break, but I don't want it. No, it's interesting now. Let's continue. Let's just say dually, a dual basis. Sorry. Mm, to put an alarm. Okay, later.
finished up our discussion of covectors. In this video, we're going to be talking about our third example of a tensor, which are linear maps. So linear maps are transformations that take a vector as an input and produce some new vector as an output. So just like I did with vectors and covectors, to introduce linear maps, I'm going to start with a coordinate definition where linear maps are arrays of numbers. Then I'm going to give a geometrical definition where you can think of linear maps in terms of pictures. And finally, I'm going to give you an abstract definition, which is purely algebraic. And in some sense, this is the best or the truest definition of linear maps. So I'm going to introduce these definitions, and I'm also going to show you how they are all related to each other. So the coordinate representation of linear maps ends up being matrices, a matrix being a two-dimensional array of numbers. So just as column vectors are the coordinate representation of vectors, and row vectors are the coordinate representation of covectors, matrices are the coordinate representation of linear maps. So let's take a look at how matrices transform vectors. So here we have a 2x2 matrix acting on a 2x1 column vector. And the way we determine the output vector is we use the standard matrix multiplication rules. So what that means is first we take the dot product of the column vector with the first row of the matrix, and then we take the dot product of the column vector with the second row of the matrix, and the output ends up being the column vector 2, 0. Now, it might be confusing to understand what a matrix is doing just by looking at the numbers inside the matrix, but there's an easy interpretation for what all these numbers mean. Notice that if I use the column vector 1, 0 as the input, I'll get the first column of the matrix as the output. And if I put in the column vector 0, 1 as the input, I'll get the second matrix column as the output. Now these column vectors 1, 0 and 0, 1, these are sort of like copies of the basis vectors E1 and E2. And I say that these are like copies because of this very important point here. Linear maps transform vectors, but linear maps do not transform the basis. So when we transform vectors using a linear map, the basis isn't changing. We aren't moving the basis. While the output vector might be different than the input vector, we're still going to be measuring the output vector using the same basis. But with that said, with matrices, the ith column tells you where to map a copy of the ith basis vector. So let's take a look at that visually. So here we have a basis E1, E2, and vectors v and w, which are sort of like copies of the E1 and E2 basis vectors. And here we have a matrix with the first column 5, 3, and the second column -1, 4. So where would this matrix send the vector v, which is like a copy of the first basis vector? Well, we just look back at the first column of the matrix, which represents the vector 5e1 plus 3e2, and that's what the output of the linear map looks like for v. So L of v is equal to this vector here. And if we ask what this matrix does to w, which is a copy of the second basis vector, well, that's just the second matrix column, which gives us -1e1 plus 4e2, and that vector looks like that. So that's L of w. And once again, note that the basis vectors haven't moved because linear maps don't change the basis. We're still measuring the output vectors with the same basis. Okay, so matrices are the coordinate interpretation of linear maps. Let's try and get a more geometrical definition. So the geometrical definition says that linear maps are spatial transforms that keep lines parallel, keep lines evenly spaced, and keeps the origin stationary. So to get an idea of what that looks like visually, let's start with a 2D space here with a bunch of grid lines overlaid on top. And here we have 3 examples of linear maps. So this linear map is basically a stretch in the horizontal direction. This linear map here is like a rotation. And this linear map is doing a sort of a skew transformation, which you could think of as maybe like a rotation in this direction followed by a stretch along this axis. And as we can see in all of these cases, the grid lines in the output space are still parallel to each other. They're all evenly spaced, even if the spacing might be different than the input space, and the origin hasn't moved. So these are examples of the types of things that linear maps can do, and I'll just mention quickly here that translations are not actually linear maps under this definition. Even though translations keep grid lines parallel and evenly spaced, translations do move the origin, so translations are not actually true linear maps. Okay, so that's a geometric definition that we can visualize. Finally, I'm going to give an abstract definition, which, as usual, might seem confusing at first, but it's actually the best definition that we can give. So abstractly, a linear map is a function which maps vectors to vectors. So in this case, we have a linear map L mapping vectors from a vector space V to a vector space W. A lot of the examples I've shown and will show in the future involve linear maps where the input and output spaces are the same, so maps going from V to V, but in general, the input and output spaces can be different. And also, linear maps obey these two properties here, that we can add the inputs or add the outputs of the linear map and get the same answer. And also, we can scale the input or scale the output and also get the same answer. And so this is the same thing we had with covectors, and these two properties here are called linearity. So both covectors and linear maps are linear functions. The only difference is that covectors output a scalar and linear maps output vectors. Okay, and you might ask, how the heck did people come up with this abstract definition? The other two definitions seem a little more concrete, but this one seems to come a little bit out of nowhere. So I'm going to show you how the abstract definition relates back to the other definitions that we saw. So here we have this abstract property of linear maps that says we can add the inputs or add the outputs and get the same answer. So to show the geometrical meaning of this, I'm going to draw the input vectors on this grid. So here we have the vector v in green and the vector w in purple, and there's some v plus w I'll write in black. Now here are those three examples of linear maps which I showed: the stretch, the rotate, and the skew. And I'm going to show you how these three linear maps obey this algebraic property up here. So first I'll draw the green vector v in all these output spaces. So basically I'm going to stretch v, addition law still works, add along. And I'm going to do the same thing for the scaling rule. We can scale, and I'm also, as you can see, the scaling rule in the output space is still obeyed. So scaling and then transforming is the same thing as transforming and then scaling. So this abstract rule just describes the transformations we've been talking about all along. So hopefully we can see how the abstract and geometrical definitions are related to each other, but we still don't really understand where the coordinate definition comes in. So this formula for matrix multiplication, it can seem really weird if you don't know the reasoning behind it. And it turns out that the matrix multiplication rule actually comes from this abstract definition that we introduced before. So to show that, let's start off by saying that we have a linear map L that acts on a vector v to produce some output vector w. And if we expand the vector v into its components, we get this. And by applying the linearity rules of L, we get this. Now, this L of E1 and L of E2, these are just vectors, right? So we might ask, how can we express these vectors in terms of the basis E1 and E2? And I'm kind of making a simplifying assumption here. I'm assuming that L is a function from V to V, so the input vector space is the same as the output vector space. So since the output vector space V still has the basis E1 and E2, that means we can still write these output vectors as linear combinations of the same old basis E1 and E2. So I've done that here, and the coefficients of these linear combinations, L11, L21, and so forth, these 1s and 2s are just labels. So I've chosen to write one label on top and the other label on the bottom for a reason. I'll get to why I did that later. But the important thing is that these L coefficients help us build up the output vectors of the linear map using the E basis vectors. All right, so I can rewrite the output vectors as linear combinations of the basis, and I can switch things around here to group the terms by basis vector. And now, since I have W written as a linear combination of the basis vectors, these coefficients are really just the components of W, W1 and W2. And so now we've derived how to transform the V coefficients into the W coefficients using these formulas here. And these formulas here, these are really just what you get when you do the standard 2x2 matrix multiplied by a 2x1 column vector. Okay, so to sum all that up, if we have a linear map L that transforms a vector V into another vector W like this, where W can be written as a linear combination of basis vectors, And we know how L transforms basis vectors, or maybe it would be better to say we know how L transforms basis vector copies using these L coefficients. And so that means we can transform the V components into the W components using these formulas here. And if we repeat this argument for any number of dimensions, if we have a linear map L in n dimensions, we would get all the L coefficients from this formula here. Then we can transform the V components into the W components using this formula here. And once again, this formula that we've derived is just the standard matrix multiplication formula for multiplying matrices and vectors together. So what we've done is we've derived the matrix multiplication formulas just from the abstract linearity properties of linear maps. So if you've ever wondered why the matrix multiplication formula works the way it does, it's just the direct result of the abstract linearity properties of linear maps. All right, so that sums up what linear maps are. Next, I'm going to talk about the transformation rules that linear maps undergo when we change basis. In this video, we're going to go...
Right.
over the transformation rules that linear maps obey when we go from one basis to have a linear map given by this matrix obey when we this matrix here, and this is expressed in the E basis. And as a reminder, this linear map turns E1 into 0.5 E1, and it turns E2 into 2 E2. So those are just the outputs of the linear map, but remember, the basis isn't changing. We're still measuring the outputs of the linear map using the same basis. Okay, so let's say that we have this vector V with components 1, 1, and L transforms V into this vector here. So what would be the components of the vector L of V? Well, to figure that out, we just multiply the column vector that represents V by the matrix that represents L, and we'll get the components 1/2, 2. So the components of L of V are 1/2, 2, and all of that is done in the E basis. Now remember, if we take V's components in the old basis and apply the backward transform, we can get V's components in the new basis. And remember, we're using the backward transform since vector components are contravariant. So from here we might ask, what are the components of the output vector in the new basis? Well, we can't use this matrix anymore since that only works in the old basis. So what we need to do is we need to find a new matrix that tells us how to build output vectors using the E tilde basis vectors. So we need to figure out these L tilde coefficients here. Okay, so let's try and figure this out. So we're taking L of E I tilde and we're writing the output vector as a linear combination of the E tilde basis vectors using these L tilde coefficients. Old base. Now we rearrange the sums a little bit. And now we rewrite the old basis vectors in terms of the new basis vectors using the backward transform. And so we rearrange the sums one more time to get this. And so on the left here, we have a linear combination of E tilde basis vectors using the summation index Q. And on the right, we have a linear combination of the E tilde basis vectors again, but with the summation index L. So we have a linear combination of E tilde basis vectors on both sides, but with different summation indexes. But really, our choice of letter for the summation doesn't really matter, right? We could choose any letter we wanted. So what I'm going to do is I'm just going to change all these Q's to L's. And now we can see that these L tilde coefficients are equal to all of this here. So really what this is saying is that to transform the matrix coordinates from the old basis to the new basis, we multiplied the old matrix by the backward transform on the left and by the forward transform on the right. So matrices or linear maps transform with both the forward transform and the backward transform, and I'll show you why that makes sense. So the L tilde matrix takes us from the input vector components to the output vector components in the new basis, right? So instead of traveling along this arrow here using the L tilde matrix, we're sort of going to go in a roundabout way like this. So to travel along this arrow to transform the new vector components into the old vector components, we use the forward transform. And here to transform the components of the input vector into the components of the output vector in the old basis, we just use the matrix L. And finally, to get from the old vector components to the new vector components for the output vector, we use the backward transform. So moving along this arrow, which is multiplication by the L tilde matrix, is really the same thing as moving along these three arrows, so forward and then L and then backward. So the idea of transforming matrix components using both the forward and backward transformations makes sense. So let's see how this works in practice. So here, to get our matrix L tilde in the new basis, we start with the matrix in the old basis and multiply on the left by B and on the right by F. So if we churn through all these multiplications, we get this matrix here, and this tells us how to write the outputs of the linear map as linear combinations of the new basis vectors. So let's see if that worked. We want to transform these new basis vector components. So let's apply the new matrix we just got, and we get the components 9 over 8 and 7 over 2. So let's just check if that makes sense. Let's measure L of V using the new basis. So it looks like slightly more than 1 E1 tilde is necessary, so that is about 9 over 8. And we need about 3.5 E2 tildes, and 3.5 is just another way of saying 7 over 2. So it turns out that this new L tilde matrix does transform vector components in the new basis. So this matrix does do what we want. Now I want to do one thing before ending this video that will make your life easier. So just remember this derivation that we did here to transform matrix components. I would say this is all pretty ugly, right? There's a ton to write out. We have to run out a ton of summation signs. So it's really not very fun. But fortunately, there's a way to make all of this much, much easier. And the key is to notice something interesting about summations. Notice that up here, this summation is over k. So we have k up top and k down low here. And notice that this summation is over j. And again, we have j up top and j down low. And same thing over here, we have a sum over L, so L up top and L down low. So it turns out that anytime we have an index letter on top and on the bottom, we end up summing over that index letter. So really, we don't need to write out any of these summation signs at all. We can just sort of pretend that they're there, because when we see an index repeated on the top and bottom, we know that there's a summation that's going to happen. So let me show you, using this notation of dropping the summation signs, how much easier that this will make our lives. So let's try this derivation again, but this time not writing the summation going here, and now using the linearity of L. And now we use this definition for the L coefficients, and we invoke the backward transform, and we change this summation index from Q to L. that's it, we're done. So look at how much space we saved here. In the derivation before, we took up the entire slide, but look at all of this blank space. Now, using this new trick of just dropping the summation signs, this derivation becomes a lot easier and a lot more clear. And I'm going to show you another trick that's actually going to make our lives easier. Let's consider what happens when we multiply a matrix M by the identity matrix. We should just get back M as the output, right? Well, let's consider the components of this matrix. Let's look at the components I, K of the matrix M times identity. So this is just the multiplication of the M and identity matrices, right? Because B components of it, with the I on top and the K on the bottom. So let's use all the tricks that we've learned just now and derive the backward transform for matrix components. So we have the forward transform here, where we move from the old components L to the new components L tilde, and we just have to remember here that the forward and backward matrices multiply to give the identity, or the Kronecker delta. So we want to get the normal coefficients L isolated on one side, right? Well, to do that, we need to get rid of the B and the F. And we can do that by multiplying on the left side by F and on the right side by B, because F's and B's should cancel out, right? So let's just do that now. We multiply both sides by F on the left and by B on the right. Now these would cancel to give us the Kronecker delta SK, and these would cancel to give us the Kronecker delta JT. Okay, so we're left with two Kronecker deltas on the right side of the equation here. Now remember, the Kronecker deltas are like summation index cancelers. So here, this Kronecker delta cancels out the J index, so we're left with T on the bottom. And this Kronecker delta cancels out the K index, so we're left with S on top. And we're done. So in just 5 lines, we've managed to convert the forward transformation for matrices into the backward transformation. So this trick of leaving out summation signs is super useful. It makes writing things out a lot easier. And we call this way of writing out tensor components Einstein's notation. So we're going to be writing tensors out in Einstein's notation like this from now on, because of how easy it makes our lives. Okay, now to sum up everything we've learned so far, we learned that basis covectors, as well as vector components, transformed using the contravariant law. And from now on, we're going to be calling these 1-0 tensors. And we also learned that basis vectors and covector components transformed using the covariant law. And from now on, we're going to be calling these 0-1 tensors. And just now, we learned that linear maps transform using both the forward and backward matrices. So in a sense, they're both contravariant and covariant. And because of that, we're going to be calling them 1-1 tensors. So that finishes up linear maps. In the next video, we're going to give our final example of a tensor, which is the metric tensor. In this video, we're going to give our final example of a tensor in this video series, which is the metric tensor. The metric tensor is something that helps us measure lengths and angles.
So for so far, we've seen linear transformations where it is like taking the basis element and sending it to the first column, and the other basis element to the other column. And because each vector can be dissected into its basis elements, so we can use this matrix notation of the linear transformation in order to send an arbitrary vector into where this L takes us. We also looked at what happens when we change basis vectors, because the linear transformation does not change the basis vectors, it just changes the coordinates, meaning it sends a vector to another vector, but the way of representation of those vectors remains the same. So it does not change how we represent the vectors. Just which vectors being sent to where. And then if we want to change the basis, so we look at this L tilde, and we did it step by step. And our way of doing that was using the forward from the left side and the backward from the right side, and peeling it like step by step. And okay, so now we continue with the examples of tensors, because the standard vectors were contravariant. They were called 1,0 tensor, because the normal the covectors were covariant. It was called 0,1 tensor. And now we looked at the linear transformation. It's 1,1 tensor. Let me verify it.
In this video with T covariant law. And from now on, we're going to be calling these 0, 1, 10. And because of that, we're going to be calling them...
So 1,1 tensor for the linear transformation. Good. Now we will look at the metric tensor.
In this video, we're going to give our final example of a tensor in this video series, which is the metric tensor. The metric tensor is something that helps us measure lengths and angles in space.
For now, the clock was ticking, so we will stop for a minute, and we take a 10-minute break. Okay, so I need a few more minutes. There is some kind of documents in order to do. Just a second. Sorry, I was talking with a friend and finished with these documents. So now let's continue. We'll see the metric tensor.
So to start off, I'll ask the question, how do you get the length of a vector? So let's say I have this vector v living in this two-dimensional space here with the following components. How do I get its length? So we can think of the vector v as the longest side of a right-angled triangle whose other two sides are parallel with the basis vectors e1 and e2. And if you remember your elementary school math, seeing a right-angled triangle should make you think of Pythagoras' theorem, right? So c squared equals a squared plus b squared, where c is the longest side of a right-angled triangle. So in this case, a is the side length along the e1 direction, and b is the side length along the e2 direction. And given the column vector 1, 2, this ends up being 1 squared plus 2 squared, which is 5. But that's the square of the length of v. So to get the actual length, we have to take the square root, and that gives us the square root of 5, which is approximately 2.236. So that's computing the length in the old basis. Let's try computing it in the new basis. So we can try going through the same process here using the components in the new basis, which are 5/4, 3. But applying those to Pythagoras' theorem, we get that the squared length is 169/16. And taking the square root of that, we get exactly 3.25. So what's up here? Why didn't this work? Why didn't we get the square root of 5 like we were expecting? And the reason we messed up, of course, is that we used the side lengths of this triangle here, where one side is given by v, and the other two sides are parallel to e1 tilde and e2 tilde, and that isn't a right-angled triangle. So really, Pythagoras' theorem is a bit of a lie for non-orthonormal coordinate systems. Okay, it only works when the basis vectors have length 1 and are at right angles to each other. So it's not really a lie, but Pythagoras' theorem only works for getting vector lengths in the very special case where we have an orthonormal coordinate system. And this fact isn't really that surprising. In fact, if we play around with different coordinate systems where a vector v is always parallel to one of the basis vectors, it becomes pretty obvious that this formula, Pythagoras' theorem, doesn't work. So in this a coordinate system where the basis vector a1 is the same length as v, Pythagoras tells us the squared length of v is 1. And in this b coordinate system where b1 is shorter than v, Pythagoras gives us a squared length of 4. And in this c coordinate system, c1 is longer than v, and Pythagoras gives us a squared length of 4/9. So we know that in the case of general non-orthonormal coordinate systems, Pythagoras' theorem is no good to us. So what do we do? So it turns out that the real formula for vector length isn't given by Pythagoras, it's given by the dot product. So the squared length of the vector v is equal to v dot v. And expanding v out in the old basis, we get this. And we can distribute this just like we would a normal algebra expression involving multiplication. So we just group the terms for first, outer, inner, and last. And so we get this. And simplifying this a little, and using our knowledge that e1.e2 is the same thing as e2.e1, because the dot product doesn't care about the order of the inputs, we get this formula for the length here. And of course, this also applies for the new coordinate system. We can just replace the e basis vectors with the e tilde basis vectors, and we replace the v components with the v tilde components. Okay, so let's give these formulas.
So if E1 is orthogonal to E2, then the middle part will be 0 because the dot product of vector that are perpendicular to each other is 0. But if they are not, then we will have something else.
Just replace the e basis vectors with the e tilde basis vectors, and we replace the v components with the v tilde components. Okay, so let's give these formulas a try. So writing it out in the old basis again here, And since the old basis is an orthonormal basis, we can use this rule here where EI dot EJ gives us the Kronecker delta. And that means when the indices are the same, we get 1. So E1 dot E1 and E2 dot E2 both give us 1. And when the indices are different, we get 0. So E1 dot E2 goes to 0. And what we're left with is Pythagoras' theorem, right? C squared equals A squared plus B squared. So the real formula for vector length is up here. But since this is an orthonormal coordinate system, all of these dot products work out to really simple answers, and we get a much simpler formula, which is Pythagoras' theorem. But of course, that wouldn't work down here in the new basis, because the basis dot products are going to work out to be different numbers. So to compute these dot products, we can just replace the set of new basis vectors with linear combinations of the old basis vectors using the forward transform. So we can write E1 tilde dot E1 tilde as this here, and churning through the math, we get this. And we can set these two dot products to 1 and this dot product to 0 because the old basis is orthonormal. And so we get E1 tilde dot E1 tilde is equal to 5. And we can do the same thing with E2 tilde dot E2 tilde, and we get 5 over 16.
Just a second.
And finally, we can do the same thing for E1 tilde dot E2 tilde, and we get negative 3/4. So we've computed all three dot products that we need right here with the new basis, and that means we can plug them into the formula for the squared vector length here, and we end up with this formula here. So this is the formula for computing the vector length in the new basis. And we can sort of think of this as Pythagoras' theorem for the new basis, where we have an additional term and different scaling constants. So let's plug in the components of V in the new basis to our formula for the squared length of V. And if we churn through all this, we see that we get 5. And so, of course, the length of V is the square root of 5, which is the answer that we're expecting. So this formula where we compute V dot V actually gives us the right answer for the squared vector length in all coordinate systems. And if we go back to our examples here, we can see why this new formula works in general. The reason is that when a vector's components get bigger, the basis vectors are going to get smaller. So when we're going from A to B here, the components are growing from 1 to 2, but B1 dot B1 will shrink compared to A1 dot A1. So the growing of the components and the shrinking of the dot product of the basis vectors is going to balance out, and the length will be the same. And the same thing applies over here. When the components shrink, this dot product of the basis vectors will grow to balance things out, and the length will stay the same. So we have these formulas here for the squared vector length, and you'll notice that we can write this formula for the old components as a series of matrix multiplications like this. And if you work this out, you still get V1 squared plus V2 squared. And the same goes for the new coordinate system. We can write this equation as this set of matrix multiplications here. And so really, the key to getting a vector length in any given coordinate system is this matrix here. And this is what we call the metric tensor. And we denote the metric tensor by the letter G, oddly enough. So this is the metric tensor in the old basis, and this is the metric tensor in the new basis. It's the same metric tensor, it's just represented by different matrices, right? Just like with vectors, metric tensors are invariant, but they look different and have different components when we use different coordinate systems. So at the end of the day, to get vector lengths using these formulas, we really just need to know the basis vector dot products. And we can store these dot products in a matrix, which represents the metric tensor for that coordinate system. So to get the squared vector length, we can just use these simple formulas here. And remember, there are implied summations over I and j here. And again, the metric tensor components are given by the dot products of the basis vectors. So earlier I said the metric tensor helps us measure lengths and angles in a space, and I've shown how it can measure lengths, so now I'll show how it can measure angles. So to start, we'll have our old basis, which is orthonormal as usual, and for this new basis here, we're just going to rotate the second basis vector a little bit so that it forms some angle theta with the first basis vector. So what I'm saying here is that E1 tilde is equal to E1, and E2 tilde is equal to cosine theta E1 plus sine theta E2. Because recall, sine and cosine are just given by this triangle here, where sine is opposite over hypotenuse and cosine is adjacent over hypotenuse. And the hypotenuse in this case has length 1, because it was a normal vector that we just rotated. So let's compute the basis dot products in this new basis. We find that first dot first is equal to 1. We find that first dot second is equal to cosine theta. And we find that second dot second is equal to 1. And I figured this out using the well-known trig identity here. Cosine squared plus sine squared is equal to 1. Okay, so we have our dot products, and that means that we can get the metric tensor for this matrix in the new basis, which we have here. And remember, this is the same metric tensor, it's just that it has different components in different coordinate systems. Okay, so let's say we have two vectors, v and w, and we want to find the angle theta between them. Well, what we can do is we can define some new basis where the basis vectors are pointing in the same directions as v and w, except that the length of these basis vectors are 1, so they're normal vectors. And now we can compute the dot product v dot w. And really, v is just some multiple of e1 since they're aligned, and w is just some multiple of e2 since they're aligned. So we can write v dot w like this. And now rearranging things, and recall that we determined when two basis vectors of unit length are at an angle theta, their dot product is just cosine theta. And finally, we just need to realize that A is really the length of V and B is really the length of W, because we need A copies of E1 tilde to get V, and we need B copies of E2 tilde to get W, and so we get this. So what we've determined is that using only dot products, since these vector lengths are also given by dot products, we can compute the angle between any two vectors that we like. So this dot product, v dot w, we can just churn through the math and we can see that we can write it in terms of the metric tensor. So all these dot products between v and w can be computed using the metric tensor. And that means that this formula here for the angle between any two vectors can be computed entirely in terms of the metric tensor, along with the vector components. All right, so hopefully we understand what the metric tensor is used for. Now I'm going to talk about how the components of the metric tensor transform when we change coordinate systems. So this is really easy to figure out. We just get the metric tensor components in the new coordinate system using these dot products involving the e tildes. Now using the forward transform, we can write these in terms of the old basis, and we get this dot product. And those are just the components of the metric tensor in the old coordinate system. So we get this transformation rule where we go from old to new using two forward transformations. And likewise, for the inverse process, to get from new to old, we use two backward transformations. And using these transformation rules, we can go through really quick here and confirm that the squared length of a vector remains constant over all coordinate systems. So we start with this formula for the squared length in the new basis. Then using our transformation rules to move from the new to the old coordinate system, we can transform the vector components as well as the metric tensor coordinates back to the old basis using the rule we just learned. And we find that we get two forward transformations and two backward transformations. And these both cancel out to give us two Kronecker deltas. And using the index canceling rule for Kronecker delta, we find that we just get this formula here, which is exactly what we are expecting for the old coordinate system. So in fact, this formula using the metric tensor works in all coordinate systems, and the vector length will stay constant. So summing up everything we've learned in this video series, we've learned about the contravariant transformation rule, and this applies to basis covectors and vector components, and they're called 1-0 tensors. We've learned about the covariant transformation rule, which is used for basis vectors and covector components, and we call those 0-1 tensors. We've learned about linear maps, which are 1-1 tensors, and those transform using one contravariant rule and one covariant rule. And finally, we learned about the metric tensor, which is a 0-2 tensor because it transforms using two covariant rules. So way back at the beginning of this video series, I gave you this definition of tensors. I said that tensors are objects that are invariant under a change of coordinates and have components that change in some special predictable way under a change of coordinates. So you're finally ready for me to tell you what this special predictable rule is. The transformation rule that tensors will obey is this. So this probably looks really complicated, but all it's saying is that if we have some object with components, and some of those components are upstairs, which are the contravariant components, and then some components are downstairs, which are the covariant components, the way we transform them is just by applying a series of forward and backward transforms. So in the forward direction, going from old to new, all these upstairs indices will transform using the backward transformation, like these ijk's, and the downstairs indices will transform using the forward transformations, like here with the rst's. And the reverse transformation from new to old, it's the same thing but opposite. We replace the forward transforms with backward transforms, and we replace the backward transforms with forward transforms. So anything that follows these rules when changing coordinates, whether it's with one transform or whether it's with 20, anything that follows these rules is a tensor. And I've already sort of hinted at this, but just to make it clear, when a tensor has m upstairs contravariant indices and n downstairs covariant indices, we call that tensor an mn tensor. So these two numbers are called the tensor's type, and they tell us how many contravariant and covariant rules we need to follow when transforming a tensor. And the last thing I'm going to say, you may recall this other definition I gave for tensors, where I said that tensors are just collections of vectors and covectors combined using the tensor product, and I told you that this was the best definition for tensors that we can come up with. So we know what vectors are, and we know what covectors are. Now what we're going to do is we're going to go through an explanation of the tensor product. And once we understand what the tensor product is, we'll understand this best definition of tensors here.
Great.
Hey everyone. So my original plan with this video series was to do 2 more videos on the tensor product and just leave things there. And that would be the end of the video series, or at least the end of the videos that don't involve calculus. But thinking about things more, I realized that I needed to spend a little more time on the tensor product in order to explain it properly. And part of that involves doing this short video, which you can see is on bilinear forms, which are another type of tensor. But this video won't be too long because you've already seen a bilinear form before. The metric tensor is actually a very specific example of a bilinear form. But I wanted to talk about bilinear forms in general before moving on to the tensor product. So we'll talk about bilinear forms really quick, and then we'll get started on the tensor product. So just to quickly review the metric tensor is a tensor whose components in a given vector basis are given by the dot products of the basis vectors. And since the dot product doesn't care about the order of the inputs, that means that the ij component of the metric tensor is equal to the ji component. So what that means is the metric tensor is symmetric about this diagonal line here. So these two triangles are like mirror images of each other. And the metric tensor can be used to get the lengths of vectors and the angles between any pair of vectors using these formulas here. So really the metric tensor is like a function that takes 2 vector inputs from a vector space V and produces a scalar as the output. So when we want to get an angle, we put in 2 different vectors, and when we want to get vector length, we put in the same vector twice. So this is the formula for computing the output of the metric tensor when it acts on 2 vectors, and we could write this out as a series of matrices like this. Now let's consider the properties of this formula. What would happen if we multiplied this entire thing by some number a? Well, we could give this a to any one of these 3 arrays, right? So multiplying this whole thing by a is the same thing as multiplying the v vector by a, and that would scale all of v's components by a. Alternatively, we could scale the w vector by a, and that would scale all of w's components by a. Now, writing everything out as arrays is kind of annoying, so if we switch to the summation notation, multiplying all this by a is the same as multiplying v by a, or multiplying w by a. And if we get a little more abstract and just look at the function and its inputs, multiplying the output of the function by a is the same thing as multiplying the first input by a, or alternatively, multiplying the second input by a. Now, I'm going to warn you now, at some point in your life, you're probably going to get the urge to do this. And don't do this, okay? You need to give the a to one input or the other, not both. In fact, if you scaled both inputs by a, that would mean the output would be scaled by a squared, right? Because you have to take both of them out in front. Anyway, that's the scaling rule for the metric tensor. Now let's consider addition. Let's say that we have two vectors that are added together like this on the left side of the metric tensor. What would we get? Well, we would just distribute this stuff to both of the vectors, right? So we'd end up with these two terms added together. And if we consider the summation notation, if we have two vectors added here, we just distribute this part to each of them. And more abstractly, if the metric tensor has two vectors added together as the first input, we could also write this as the sum of two functions, where the first inputs are each of these vectors and the second input is the same for both. And we could also consider doing the same thing, but for the right side of the metric tensor. So we have this vector sum here, and we could just distribute this part to both vectors. And in summation notation, that would look like this. And finally, in the abstract form, we would take this single function with a sum in the second input and write it as a sum of two functions, where each of these vectors become the second inputs, and the first input is the same for both. So these are the two addition rules for the metric tensor inputs. And I'm going to warn you again, at some point in your life, you're probably going to get the urge to do this. Don't do this, okay? This isn't right. If we want to sort this out, we need to follow these rules up here one at a time. So we can start by distributing the first input to get these two terms, and then we can distribute the second input in each of these, like so. So there are 4 output terms in total here. So please try to remember that. Okay, so we have the properties of the metric tensor up here. It's a function that takes two input vectors from a vector space V and returns a scalar. The scaling rule tells us that we can scale the output or scale either one of the inputs, and the two adding rules tell us that when we have a vector sum in one of the inputs, we can distribute the vectors in the sum while holding the other input constant. And in a given basis, we compute the output of the metric tensor using this formula here. Okay, so now it's time to define bilinear forms. And the definition of bilinear forms is actually everything we just stated up here. So a bilinear form is a function that takes two inputs from a vector space V and returns a scalar output, and it follows these adding and scaling rules here. And just like the metric tensor, to compute the output of the function in a given basis, we use this formula where B, I, J are the components of a matrix. And just like the metric tensor, bilinear forms are 0-2 tensors, so they transform using two covariant rules when we change coordinate systems. Okay, so why do we call these bilinear forms? So I'll start with the word form. A form is basically just a function that takes vectors as inputs and outputs a number. So covectors are also sometimes called linear forms because they are forms that follow the linearity properties. And we also sometimes call them one forms since they take one input. So bilinear forms, or sometimes called two forms, obviously they are forms since they take two vector inputs and output a scalar, but let's be specific about what we mean when we say bilinear. So if you look at the bilinear form rules and focus only on the rules that involve the first input and pretend the second input is fixed, so it's like it's locked away in stone and will never change, B looks an awful lot like a covector or a linear form, right? We can scale the input or the output and get the same answer, and we can add the inputs or the outputs and get the same answer. Alternatively, if we focus only on the rules that involve the second input and pretend the first input is fixed and locked in stone, B also looks like a covector or a linear form, where we can add or scale the inputs and outputs and get the same answer. So when we say that B is a bilinear form, it's because it's a form where each individual input is linear while the other input is held constant. Now, so far, I've made it seem like metric tensors and bilinear forms are the same thing, right? Because they both obey two covariant transformation rules and they have similar properties. But they're not actually the exact same. So what's the difference between them? So as I said before, the metric tensor is a bilinear form, but it's a very specific example of a bilinear form. In fact, the metric tensor has two extra properties that other bilinear forms might not have. So remember, since the metric tensor components are symmetric, we can swap I and j here, and this actually means that the order of the input vectors in the metric tensor doesn't matter. So with the metric tensor, we can swap the inputs without changing anything, but we can't necessarily
So
do
it's
that
not
with
something
bilinear
that
forms.
happens. Okay,
Another thing
in
is that
general,
since
right
the
now.
metric tensor measures vector lengths, when we put the same vector in twice, we always get an answer that's greater than or equal to 0, right? Because it doesn't make sense to get a negative squared length as the output. But again, this isn't necessarily true for some bilinear forms. So certain bilinear forms are valid metric tensors and others aren't. So some examples of bilinear forms could be valid metric tensors. For example, these two matrices that we talked about in the previous video, these are valid metric tensors because you'll notice that they have symmetric matrices. And also, when we put the same input in twice, we'll always get answers that are non-negative. So you can try whatever V1 and V2 you like in these formulas. The answer will always be positive or 0. It's impossible to get a negative number. But on the other hand, some examples of bilinear forms aren't valid metric tensors, as we have over here. So this first example obviously isn't symmetric, so it's not a valid metric tensor. And over here, while this matrix is symmetric, it's possible to get a negative output if we choose V1 and V2 correctly. So for example, the input components 1, 1 would give a result of -8. So metric tensors are a very special example of bilinear forms. Basically, if this box is the set of all bilinear forms, this smaller green box aside would be the set of all metric tensors. So just to repeat everything once more, bilinear forms take two vector inputs and output a scalar. They follow these adding and scaling rules, and we compute their output in a given basis using this formula. And finally, their components use two covariant transformation rules when we change coordinates. Alright, so I've spent a good 10 or so videos talking about a whole bunch of different types of tensors. We've got vectors, covectors, linear maps, bilinear forms. We've got all these tensors and all these transformation rules. So now it's time to level up. So this video marks the beginning of a bit of a shift in this video series. We're going to stop talking about new types of tensors and instead change the way we think about the tensors that we've already seen. So recall I proposed this better definition of tensors, where rather than defining tensors in terms of transformation rules, we define them as collections of vectors and covectors combined using the tensor product. And the reason this definition is so good is because it's going to help us simplify our lives. A lot of the things that we learned in the previous videos, we can sort of forget about because it's going to come naturally out of this new definition. So what we're going to do here is we're going to introduce the idea of the tensor product, and we're going to upgrade our definition of tensors to something new. And this new and different perspective is going to give us a better understanding of what tensors are. So in this video, I'm going to take the first step into introducing the tensor product, and that first step is talking about what I call vector-covector pairs. And I'm just going to warn you that I'm going to use some non-standard notation that I made up just for these videos. So some of the things that I write down in the next few videos, you're not going to find it written that way in textbooks or other articles you'll read online. Okay, so we're saying that tensors are collections of vectors and covectors combined together using the tensor product. Now, we've already learned about vectors and covectors, and according to that definition, all other tensors are just vectors and covectors combined together. So vectors and covectors are like the fundamental building blocks for all other tensors. Now, that makes us think that these other tensors over here, linear maps and bilinear forms, It makes us think that these can somehow be built out of vectors and covectors, and that's exactly correct. So let's see how we can build linear maps out of vectors and covectors. So we already know that when we multiply a row vector and a column vector like this with the row vector first, we end up with just a scalar. But if we reverse the order and put the column vector first, we'll get something different. So instead of a scalar, we'll end up with a matrix, and the entries of that matrix would be these here. Okay, so we have a matrix, and a matrix is basically a linear map, right? So there we go. We've combined a vector and a covector together to get a linear map. So this method of combining column vectors and row vectors is sort of the first step to understanding the tensor product, but we'll need to explore it a bunch more before we can say what the tensor product is. So to go a bit deeper here, I'm going to get you to consider something. Let's say that we have this linear map here represented as a matrix with the components 4, 400, 8, 800. Now, can we go in the reverse direction? Can we figure out the right components A, B, C, D that would break this matrix back up into a column vector and a row vector? So if you want, you can pause the video and give this a try, but I'm going to go ahead and give the answer. So if we have the column vector 4, 8, and the row vector 1, 100, we can multiply them together to get this matrix here. Okay, so now consider this example where we have the same matrix, but the 800 has been changed to a 1200. Can we do the same thing and break this matrix up into a column vector and a row vector? And you can try as hard as you like, but it turns out that this is impossible, and I'll prove that to you. So if we want to separate this matrix into a column vector and a row vector, the matrix elements have to be equal to AC, BC, AD, and BD. And so following that reasoning, that means that AC has to be equal to 4, BC equals 8, AD equals 400, and BD equals 1200. So the first thing to realize is that these two first equations tell us that B is equal to 2A. So I'll show that here. If you just follow this reasoning, you'll get that B is equal to 2A. And we can apply similar reasoning for the second two rows here. If we just do some substitutions and follow the reasoning, we can show that B equal to 3A. So how can B be equal to both 2A and 3A at the same time? Well, that would imply 2A equals 3A, and that means that A has to be equal to 0. And that obviously isn't true, otherwise the entire first row of this matrix would need to be 0, and it's not. So this A equals 0 is a contradiction here, and what that means is it's impossible to solve for A, B, C, and D in such a way that this column and this row will multiply to get this matrix. So what we've learned here is that there are some matrices that can be broken up into column vectors and row vectors, and other matrices can't be. So we have two categories of matrices here, and these are called pure and impure matrices. So pure matrix components can be written as a product of column vector and row vector components like this, whereas impure matrix components can't be written as this product. So here are a couple examples of pure matrices here, and it turns out that pure matrices are actually really boring when they're used as linear maps. And that's because all the output vectors exist along the same direction. And the reason for that is you'll notice that with pure matrices, the columns of the matrix are all scalar multiples of each other. So 4, 8 multiplied by 100 gives us 400, 800. And 1/2 1 multiplied by 2 gives us 1, 2. And recall that since the matrix columns tell us where each basis vector copy goes when it's put through a linear map, if all the matrix columns are multiples of each other, that means that all the basis vectors give outputs that point in the same direction. And that means that all possible vector inputs going through the linear map are sent to the same direction. So that's why pure matrices are kind of not very interesting. The set of transformations they can do is really limited. But impure matrices are the more interesting ones. They can send basis vectors to different directions, so we can get more interesting transformations. So we have a bit of a problem here. We can construct pure matrices using column vector, row vector products, but they're the boring ones. So how can we construct impure matrices, the interesting ones, using column vector, row vector products? So what I'm going to do is I'm going to define 4 special vector-covector pairs using the old E basis and the old epsilon dual basis. So this matrix with a 1 in the top left and zeros everywhere else, this can be written as this product here, which is really just a product of E1 and epsilon 1. And we can do the same thing for these other basis vectors and covectors. We get E1 epsilon 2, E2 epsilon 1, and E2 epsilon 2. And so we have these 4 matrices here. And you'll notice that these 4 matrices, when taken in linear combination, so when we scale each matrix by a different amount and then add them all together, we can get any general 2 by 2 matrix that we like just by picking the right scaling numbers. So really, this set of 4 products forms a basis for all matrices that are linear maps from the vector space V to itself. So any general linear map L can be written as this linear combination here if we pick the coefficients right. And we can summarize this using the Einstein notation and see that any linear map L can be written using these components Lij. Now you might be thinking, all I see here is a vector and a covector written next to each other. How can this be a linear map? Well, if we think of some linear map L as a linear combination of these basis linear maps, and we also have a vector V, which is a linear combination of these basis vectors, what would we get when L acts on the input V? Well, to do that, we just substitute this in for L and substitute this in for V. And as you can see here, this epsilon dual basis vector, it's acting on the input vector. And that's totally fine, right? That's what covectors do. They act on vectors. So we can use the linearity of epsilon to take out the scaling coefficient Vk and put it out in front. And now we're left with epsilon j acting on Ek. And remember, by definition, this is just the Kronecker delta Jk. And by the Kronecker delta index cancellation rule, we can cancel out the k's and replace this with j. And finally, we get this. So this is our output vector, written as a linear combination of the E basis vectors. And these coefficients, these are just the numbers that we get from the standard matrix multiplication rule. So as you can see, this E epsilon product pair, this really is a linear map. It took an input vector, transformed it, and gave us an output vector. So vector-covector pairs really are linear maps. Now, earlier I gave you this set of 4 linear maps and said that they formed a basis for all possible linear maps from V to V. But just like with vectors, there's nothing special about this basis. We could just as easily choose another basis, right? Even though these matrices look really nice and simple, we could just as easily pick another set of basis matrices. So for example, these 4 matrices here, they all form a basis for the set of 2 by 2 matrices. And that might look pretty hard to believe, but in fact, if we choose these scaling numbers right, we can indeed get any 2 by 2 matrix that we want. And likewise, we don't have to choose this set of 4 linear maps as our basis. We could just as easily choose this set of 4 linear maps instead. So the set of new basis vector and new dual basis covector pairs. And that would be an equally valid choice of basis. So to sum up what we learned in this video, we learned that we can combine vectors and covectors to get linear maps. So doing it with arrays, we put the column vector first on the left and the row vector second on the right, and the result of that multiplication is a matrix. And we can also do things algebraically by just writing the vector next to the covector like this, and this is a linear map that can take a vector as an input just like we showed before. But the problem is that a single vector and a single covector combined together like this creates a pure matrix or a pure linear map. And those are really boring because they send all the output vectors to the same direction. So to get the more interesting linear maps, we need to combine a bunch of pure linear maps together in linear combination. And that will help us get more interesting impure linear maps. And the last thing I'll note is that these vector-covector pairs, this is actually the tensor product of a vector and a covector. I like to write them like this, but your textbooks are probably going to write them like this, with a circle times symbol in the middle. For now, I'm going to stick with this notation. I'll talk about this circle times notation more in a future video. In this video, I'm going to introduce the idea of covector-covector pairs and show that these covector-covector pairs are, in fact, bilinear forms. And also, I'm going to be using some non-standard notation for the tensor product in this video. Most textbooks will write it like this, with the circle times operator in between. I'm going to omit that symbol and just write the covectors next to each other like this. So recall in the last video, I introduced a new perspective on linear maps. I said that linear maps can be written as linear combinations of vector-covector pairs like this. And this process of combining vectors and covectors together is called the tensor product, which your textbooks will write like this. So we have this new perspective, and this new perspective came along with a lot of benefits. The first and most obvious benefit is that we didn't have to remember the linear map transformation rules anymore. We actually get them for free. So if we write out a linear map in the old basis here, and we want to move to the new basis, all we have to do is we transform the basis vectors and the basis covectors individually. So basis vectors are covariant. So to build old basis vectors out of the new basis, we use the backward transform B, and basis covectors are contravariant, so we build the old out of the new using the forward transform F. And we just pull these out in front, and there we go. These are the components of the linear map in the new basis. So as long as we know how to transform basis vectors and basis covectors, we get the transformation rules for linear maps almost for free. Another big benefit is that when we have a linear map acting on a vector, we can get the correct matrix vector component multiplication formula for free. We just have to replace the linear map and the vector with their linear combinations expanded in some basis. And by using linearity rules and the Kronecker delta index cancellation rule, we automatically get the correct components for the output vector given by this multiplication formula here. And finally, the last benefit we get, I didn't actually mention in the previous video, but if we consider tensors as arrays, the tensor product will automatically give us the correct array shape. So what do I mean by that? Well, before I showed you that when we have a column vector on the left multiplied by a row vector on the right, we obviously get a matrix as the result. But there's another way of getting this same result, and that's sometimes shown using this circle times symbol in here. And what this circle times symbol is telling us to do is, it's telling us to take the array on the left and distribute it to each of the components inside the array on the right. So distribute, that just means we take this column vector here and give one copy of it to each element inside the second array here. And so we're left with this, which if you look at it, it's a row of columns, which it's basically like a matrix. So this way of thinking tells us that linear maps are rows of columns. Now you might be thinking that this is kind of stupid. Obviously linear maps are matrices, you don't need anyone telling you that. And you're kind of right that this isn't a big surprise, but this idea of distributing arrays into each other will turn out to be very useful later on. So all of that is a summary of how our perspective change on linear maps gave us a bunch of benefits. Now next we're going to go through a similar perspective change for bilinear forms, and this of course includes the metric tensor, and we're going to view bilinear forms as linear combinations of covector-covector pairs like this. So first of all, why are we choosing covector-covector pairs for bilinear forms? Why not choose something else like vector-vector pairs? Well, bilinear forms take two vector inputs, right? And since covectors take one vector input each, a pair of covectors would take two vector inputs. So that's sort of a hint that we're on the right track with covector-covector pairs. So we'll just go through the same process again. First off, we'll look at the transformation rules. If we assume we can write out any bilinear form as a linear combination of covector-covector pairs, to get the transformation rule for these components, we just transform the basis covectors individually. So basis covectors are contravariant, so to build old from the new, we use the forward transform F, and putting these in front gives us this transformation rule, which as we can see is the correct one. And we could go through a similar process for the reverse transformation. Next, we can see that we can also get the correct component multiplication formula when a bilinear form acts on two vector inputs. So again, all we do is replace the bilinear form and the vectors with their linear combination expansions in some basis. And what we do now is we pass each of these vector inputs to their corresponding covectors. So the first vector is passed to the first covector, and the second vector is passed to the second covector. And by linearity of covectors, these come out in front, and these become Kronecker deltas, and finally, by the index cancellation rules, we get this. And this is the correct component multiplication formula that ends up giving us a single number as the result. And finally, the last benefit is the array shape. So with linear maps, we had this circle times operation with a column vector on the left and a row vector on the right. But for bilinear forms, since we're dealing with covector-covector pairs, we're going to use two row vectors instead. And again, we're going to distribute the array on the left to every element of the array on the right. And we end up with this, which is basically a row of rows. Okay, so hold on. We got a row of rows, and that might not seem right at first. Recall in a previous video, I wrote out the array multiplication like this, where this bilinear form, or metric tensor, was a matrix. So why did we get a row of rows? Well, a row of rows actually makes a lot more sense. Remember, with this formula up here, even though we have two vector inputs, we needed to write one as a column and one as a row flipped on its side to make the multiplication work correctly. And that's kind of weird, because vectors should never be written as rows. They should always be written as columns, right? Well, when we write the bilinear form as a row of rows, the matrix multiplication formula makes a lot more sense. We can write out both vectors as columns. And you'll see that if we churn through this, we get the right answer. So here's a row and a column. We just multiply them together like we normally would. We do first times first plus second times second. And now we have a sum of two rows here, so I'll just add them together. And again, we have a row and a column here, so it's the same old process, first times first plus second times second. And the final result is this, which we could write as this summation. So from an array multiplication standpoint, viewing the bilinear form, as a row of rows actually makes a lot of sense. So to summarize what we learned in this video, we learned that we can write bilinear forms as linear combinations of covector-covector pairs, and this immediately gives us the transformation rules, the component multiplication formula, and the correct array shape, all for free. In this quick video, I'd like to clarify the difference between
Okay, so we finished video 12, and so far we see ways to describe the tensor product as vector and covector pairs, and how to join them. And now I'm going to test myself with Gemini about the material so far. second.
Alright, welcome to this video series on tensors. In this first introductory video, I'm going to try and give you a bit of motivation for why you might want to study tensors.
Okay. I'll take the 10 minutes. Okay, so it's going to end soon. I will do the following. I need to teach at 12, so I will need to eat something and shower and everything. So I will do the following. I will end the stream now, and in 1400, it's 2 p.m. In the clock of Israel. I will go back to streaming and continue from where I stopped. So for now, that's it. And it was wonderful being here. And although no one was connected, I feel good that I'm starting to doing that because it gives me purpose. Okay.